Hey guys, what's going on? We've got some exciting stuff going on today. We've got some real exciting stuff. We are going to have the greatest time today. We're going to go over some computer architecture, but first, I want to thank you all for being here. We're going to have a lot of fun today. If you want to see more of this stuff, just follow me on YouTube or follow me here on Twitch. I'm going to be streaming every single day for a couple hours. And I'll try to make some YouTube videos as well. Some YouTube exclusive. YouTube's going to be where I'm going to do a lot of the pre-prepared problem solving. That way I don't look like an idiot on stream. Yeah, that's going to be fun. So yeah, I'm not going to bother you guys about donations during the stream. If you want to donate to me to get a better drawing tablet so that I don't have the penmanship of a second grader, that's what that's going to be going for. Any donations are just going to go to that and probably saving for my wedding and honeymoon. But you don't have to donate. I'm never going to put any of this stuff behind a paywall. All this stuff is going to be completely free. So okay. So the first thing I wanted to say is, I'm glad you're all here. Let's look at some of the stuff that we're going to be looking at. So here's all the courses that we're going to be doing. So that's pretty interesting, right? We're going to be doing a course on operating system concepts. So this is the dinosaur book. This is the gold standard for operating systems. So we're going to be starting this on Monday. We're going to be starting a lot of these books on Monday. So we've got operating system concepts. We have linear algebra and its applications. We have crafting a compiler, a classic, a first course in compilers. Everyone needs a first course in compilers. Digital integrated circuits. Now this one's interesting. So this is when we're actually talking about, manufacturing integrated circuits and how that works, and designing integrated circuits. This is going to be really fun. Yeah, look at this. This is cool. Okay. And then, what am I missing? Computer networks. Everybody needs a course in computer networks. Everybody needs a course. And then finally, we've got a classic, the Roth and Kinney Fundamentals of Logic Design. This is a first course book in computer engineering that many people do. Let's see, will you be streaming at this time every day? Not likely. A little bit later than this. I'm streaming from my lab, so I don't want to stream from my lab when there's people in here. I should make a strim.gg account and link your strim so it shows up at the top. I should. I need to. I haven't yet. I think I have. I don't think I did it correctly. Okay. So this first book is like I said, this is a first course book in computer engineering. So that'll be interesting. This is something that I actually went through this book. I used this book when I was first becoming a computer engineer. So you go over basic stuff, computer arithmetic, some basic stuff on binary, some basic stuff on logical gates. What else do they have in here? Some stuff on Boolean algebra. And then they get into stuff on, actual timing diagrams and state machines and state graphs. So that'll be pretty interesting. Yeah, it's pretty easy to do. Yeah, I know. I was setting it up yesterday or something, but I don't like to leave the stream for too long to start looking at, it's hard to multitask doing that kind of stuff. And listen, you guys are coming here for the educational content. So without further ado, let's get back to what we were talking about yesterday. So yesterday we went through all of chapter 1 of this book over here. Let's go to the top. The Patterson and Hennessy Computer Organization and Design, the RISC-V edition. There's a MIPS edition, and then, so this is the RISC-V. And so I'm using RISC-V just because it's fairly interesting. RISC-V is just an instruction set. It was made at Berkeley. So just to recap, let's look over table of contents from yesterday. So we saw an introduction to computers. We saw the 8 great ideas in computer architecture. These are the things we want to keep in mind. Oh, you're here for the ASMR, you're not here for the education? Listen, that's fine. Okay, so we also learned, what happens below your program. You write a program, what happens underneath on the hardware. We saw, the different technologies that are used to make all these components that go into making a processor. We looked at performance and how we quantify that, and we saw that power is becoming an increasing issue. And then we saw the more recent trends in computer architecture, which is we're moving from single processors to multi-core. That's a very common thing. We briefly skipped over this stuff, benchmarking the Intel Core i7. We can go over that some other time, but this is mainly just looking at data. So this isn't necessary for learning these fundamental concepts, but it's an interesting exercise that I leave to the watcher. Then there's fallacies and pitfalls, and so there, John Hennessy and David Patterson kind of go over, what are some common mistakes that people generally trip up on when they're first learning something like computer architecture, and then we'll go over, concluding remarks, or then we went over yesterday some concluding remarks, and then we skipped over some of the historical perspective because we already had a stream talking about the EDVAC, which is the first stored program computer. So that being said, we can go ahead and go to instructions, the language of the computer. So now we're going to get into the instruction set. Here we go. All right. Let's get started. So we'll skip over the abstract and some keywords. So here's what we're going to be going over today. So we're going to have a brief introduction on instructions. We'll see what some of the basic operations that are done with computer hardware. We'll look at the operands. We'll look a little bit at signed and unsigned numbers. That way we understand, exactly what's going on when we do arithmetic in the computer. A non-Indian computer architecture stream and video. That's absolutely right. Listen, I'm cornering the market. This is my market now. It's mine. Okay. So let's keep on going. So what do we have? So the next part, how do we represent instructions in a computer? So we saw that a little bit initially in last chapter, how we have our application code written in something like C or Java or C++. Hopefully C or C++. I don't like Java, which I think anyone that likes C or C++ usually says they don't like Java. And we saw how that gets compiled down into something like an assembly code. And so in this book, they use RISC-V for that. And then we saw that we take that assembly code and then that goes to an assembler, which turns it into machine code, which is binary ones and zeros. So then we'll look at some logical operations and what those are used for. We'll look at instructions for making decisions. So not only when we do something like an instruction, we don't always want to calculate something. Sometimes we need to make a decision based upon the result of a calculation. So we'll look at those instructions. So how do we support procedures in computer hardware? How is this data going to get back to people? So if we were able to give a computer a bunch of numbers, it's pointless if somehow we don't have a way to read that back. or understand what the computer got as a result. We don't want that to be something private. So what else is going on? So we have RISC-V addressing for wide immediates and addresses. So this is going to be something that's particular to the RISC-V instruction set. We're going to look at parallelism and instructions a little bit. So this is going to be on synchronization. This is a pretty advanced topic, so we're probably going to go into this only a little bit at first. Then we're going to look at the beginning of a program, some translation that we need to do. We'll look at an example and see some information on arrays versus pointers and how they differ and how they're similar. And then we'll look at a couple last things. These will mainly just be extras at the end if we have time. So this is going to be the difference between what happens when you compile something like C and when something like Java is interpreted. So Java is, if I'm not mistaken, runtime compiled because it runs inside of a virtual machine, which is what JVM is, Java Virtual Machine. And that's why they have the slogan "Write once, run anywhere." It's because it uses this virtual machine interface instead of needing to know information about the specific lower hardware, the actual underlying hardware, I should say. And then we'll look at the MIPS instruction set, the x86 instructions. Here's a hint: if someone ever says, "Hey, I want to learn about x86 instructions," listen. Stay away. Go very far away. Don't do it. Okay. And then we'll look at the rest of the RISC-V instruction set. This should be pretty similar to MIPS, if I'm not mistaken. As always, because this is a Hennessy and Patterson or a Patterson and Hennessy book, there's always going to be a chapter on fallacies and pitfalls. And then we'll probably look at some of the concluding remarks and maybe briefly just kind of go over the historical perspective. So let's see. We have less than 100 pages to get through. If we wanted to just get through the main portion of this, we really have about 80 pages. We want to get to about arrays versus pointers, or maybe compiling C and interpreting Java. That's about as far as we need to get with this. Okay. So you guys excited? You guys ready? You guys ready to have some fun? Listen, I'm ready to have some fun. This is going to be great. So okay, let's get started. Let's get in there. So this is that picture that we saw earlier in chapter 1. You know, kind of, yeah, pointers. Pointers are fun, man. Listen, people that do Java don't like pointers, but listen, the control that you have, it's amazing. Okay, so let's look. So this is that, basic component, the 5 classical components of a computer. So you've got your control and your data path. So control basically tells the data path what to do. You have your input and output. And you have memory. So these are really the 5 things. So we want to be able to put something into the computer. We want to be able to take something out of the computer. We want to be able to store something in a computer. We want to be able to control what's going on in the computer. And we want to be able to have something to control, which would be the data path. I'm not going to lie, all I do is program in Java. Listen, that's fine. I'm not going to pass judgment on you. I'm never going to be a Java programmer. It doesn't make sense for me. It's not fast enough, and it doesn't do the things that I need it to do. Okay. So then we have these kind of outside things that we need to always be kind of cognizant of, which is the compiler and how that's going to be generating our instructions for the computer. And we also need to be able to evaluate how well our program executes on the computer. And so when we're evaluating performance, we have to evaluate not only is it something intrinsic to the computer that made an application slow, but we also need to, have some insight into maybe it was the application itself or the algorithm that is inherently not tuned for this architecture, because you can do a lot of fine-tuning of algorithms. So let's get started. So let's introduce this subject of instructions. So to command a computer's hardware, you must speak its language, and the language of a computer is going to be known as its instruction set. So your instruction set you can think of as, the alphabet. It's the building blocks of building applications. So just kind of like the alphabet is used to build words, the instruction set is used to build programs. So in this chapter, we're going to go over the instruction set of a real computer, and we're going to look at both the form that's written by people. So in this case, we're going to go over some examples of how it's written in C, how it looks in assembly, and then what the actual processor sees, which is going to be the assembly that's assembled down into the machine code, which is ones and zeros. No, I missed chapter 1. Listen, Pudgy, I have the VOD up of chapter 1 if you wanna go watch that, and I also have it on my YouTube. You can just click that link at the bottom to that YouTube, and you can go watch chapter 1 right now. It's all going on YouTube immediately after it airs. In fact, 1 and 1.5, which is basically the continuation of 1, is already up. I'll watch after chapter 2. Listen, that's perfectly fine. 1 is basically your introduction to computer architecture. A lot of the stuff there isn't necessary for what we're going to learn today. It's basically just to give some context. So let's see. So we introduce instructions in a top-down fashion, meaning that we're going to start from the notation that it looks like a restricted programming language, and then it's going to be refined step by step until it looks like an actual language of a real computer. Okay. So let's see if there's anything interesting here. So like I said, we're going to be looking at RISC-V, which was developed at UC Berkeley starting in 2010. So a lot of times, institutions like Berkeley or Stanford or MIT, they will develop these platforms that are very comprehensive. So they'll develop entire operating systems or instruction sets. So there's an operating system, I think it's called Xenu. I think it's called like XENU, and that's, I think, purely a teaching operating system. It's an operating system designed around being very simple, very limited functionality, but very good for something like teaching. So RISC-V is a lot the same way. I think it is. Maybe it might not be a teaching one though. It might be a general purpose, good for actual application. I don't know if anything uses RISC-V though. To demonstrate how easy it is to pick up other instruction sets, okay, so we're going to look at MIPS and x86 just to show that if you know one assembly language, you can reason about every assembly language for the most part. There's a couple nuances based upon instructions that may be different sizes, and we'll learn about what that means in different architectures, but the core idea is the same. Yeah, and the similarity of instruction sets occur because all computers are constructed from hardware technologies based on similar underlying principles. So this is very key to understand, is that even though you have your AMD processors and you have your Intel processors and you have any kind of processor you want, the core idea of how a processor functions is usually the same everywhere. Usually it'll just have, maybe some optimizations here or there. So okay, so let's move on. So we're going to go back to this idea of stored program. So this is something that we talked about in one of the earliest streams. Or no, it wasn't a stream. This was the first video that I posted on YouTube, or the second. It was the first or the second. I think it might have been the second. But basically, it's on EDVAC, the first stored program computer from John von Neumann's paper in 1945. And we're going to see, what that, I think that's what this is going to be kind of talking about, what that means to be a stored program computer. And so that's going to be instructions and data of many types can be stored in memory as numbers and thus be easy to change, leading to the stored program computer. So that's what the stored program concept means. So we want something that's reusable. That's all that's saying. When we're talking about something that's stored program versus fixed program is going to mean it does one thing or some set of things that's fixed. Stored program means it can do arbitrary. Okay. So we'll give a brief look at the instruction set and see if there's anything interesting here. I'll zoom in a little bit. So we have 32 registers from X0 to X31. So registers are the fastest type of memory that we can access inside of the core. So the memory hierarchy usually omits them and doesn't consider them part of the memory hierarchy. Hey, it's option selects. How's it going? We're going over computer architecture. Everyone gets to learn how to be a computer architect today. Okay. So this is kind of this is your fastest kind of memory that's in a computer, but this is something that's private per thread. These aren't shared. Maybe there's usually some instructions that actually allow you to share registers, but that's something that's not something supported in RISC. That's going to be something that's an x86 thing or some very complicated architectures. So like I said, they're very fast. And X0 is usually, a specific register that always stores 0. So this is like a constant register. And sometimes this is usually included just for convenience. That way, when you need to test something against 0, you don't always have to load in a 0 or assign some variable to 0. You have something that's already predefined as 0. So that's why we have this register X0 always be 0. So we have 2 to the 61 memory words. So that's a lot. That's pretty good. That seems very big. And those can only be accessed by data transfer instructions, which is RISC-V uses byte addresses. So when we talk about bytes, we're talking about groupings of 8 bits. That's why we have with these memory accesses, they're memory of 0, of 8. So these are all going to be mod 8. So then we have the RISC-V assembly language itself. So we see that it's not terribly complicated. It looks a little bit different than, high-level programming languages. We have to specify, there are no equal signs anymore. We still have add, subtract, add immediate. So this is a little bit different. So we have different instructions for add. And so what does that mean? So this add only adds variables. This add adds some variable, and then it also adds some constant that you can just immediately type in to your whatever editor you're using. So 20 instead of, say, X7. Then we have our loads and our stores. And so loads and stores are going to be how we actually access memory. And so we're going to, when we want to get something from memory, we're going to do a load, and we're going to give it an address. And we're going to find something that's at that address, and we're going to load it into some register. So in here, we're going to say load a word from a piece of memory at this location with some offset, and then we're going to load whatever is stored there into X5. And the same idea for store. So for store, we're going to put whatever is in x5 into whatever is in the location of memory that's at address that's stored by x6 with an offset of 40. So that's what this means here. So it's going to be memory of the address of x6 plus an offset of 40. And then we're going to assign that x5. Any questions? So this is just basic assembly type stuff. And so they can actually load things at the granularity of a byte unsigned. And then they have a couple other instructions that we won't get into right now. Did anyone do basic here? I never did basic, but I'm also not terribly old or have never had an application that has required me to learn basic, so I really never had the chance to or the reason to. So let's see what else we have. So we have a way of loading values from some immediate that we specify. And so this is this is extended out. So we know that everything in a computer has to have this fixed size that's defined. We can't make something too big or too small. So explain how these logicals work seems weird to me. Okay, so let's look at the logicals. So we have bitwise, bit by bit and, bit by bit or, bit by bit XOR. So let me get the pen out. This will help explain that. So when we're talking about AND here, we're going to say take whatever's stored by x6, whatever's stored by x7, and these two things together, and store that result in x5. Whatever is first is usually where you're storing something. So if we had something like 1 0 1 1 ANDed against 0 1 1 0, so it says it's bit by bit AND, so we just compare bits. So 1 and 0, 1 ANDed with 0, 0, 1 ANDed with 1, 1, 1 ANDed with 0, 0, 1 ANDed with 0, 0. So this is going to be what's stored in, say, x5. That makes sense? Oh, it literally tries to truth table. Yep, yep. A lot of times in computer architecture, the more you think about something, you end up getting farther away from the truth. Okay, so what else do we have? We have exclusive OR, and so that's just typically denoted by the, I don't know what you call that. I usually just call it a caret. I learned that that's just called a caret. So then you're able to do inclusive or immediate. So that means you're able to do an inclusive OR with an immediate value, so just like a constant that you say 20 instead of a register value. Then, yep, fairly simple. Then we have some shifts. We have some logical shifts. We have some arithmetic shifts. And we'll go into that later. We'll go into later the difference between logical and arithmetic shifts. But for right now, we can just think of, we're moving bits around in a very sequential way. So if we say shift something logically left by 7, it means we're moving all the bits to the left by 7. And all logical and arithmetic do is it determines whether or not we care about the sign of that number or if we're treating it as just bits and not signed bits. And so that'll probably make more sense when we go into, that'll make more sense once we start going into computer arithmetic a little more. And then we have branches and unconditional branches, otherwise known as jumps. So if we have some basic for loop, so let me write some basic for loop. So if we have for something, and then say this is 1 to 5. So once we get down here, and this is just some code, right? So once we get down here and we know that we haven't completed 5 yet, we want to go back up to the beginning. And so this is done with what's called branches. And so the program counter, so the PC is equal to something called a program counter. This is just a counter that keeps track of which instruction we're on. So in a very naive case, we'll say that we have a PC that is, say, 0, 4, 8, 12, 16. And you know, we can even do it even simpler, because this is taking into consideration the size of the instructions. We can just say it's 1, 2, 3, 4, 5. And so that, let's just say that up here we're doing something related to the for loop. We're checking something like 1 versus 5. We want to see if whatever value here, we want to see if we've gone through 5 iterations yet. This is just going to be something. These are all going to be something. And then down here, what we want to do is we want every single time we want to go back to 1. So this is going to be, we want to branch back to this program counter value of 1. So that's, is it wrong to think of PC as the line, like a number line? No. You basically just think, you can think of it as a number line, but it's important to realize that what the programmer sees is a lot different than what is actually going on. So in reality, you're executing every single instruction out of order within some window. But to the view of the programmer, everything is occurring sequentially. And so that concept is called out of order execution. And that's where we get a lot of performance from. But to the view of the programmer, everything happens sequentially. But that's not how it happens in hardware. And so that's an interesting thing that only architects really learn about. Do you know why there's a branch if greater than equal to n instead of a branch if greater than n minus 1? Seems like compiler would could optimize the need for that instruction out, but no. Let's see. So you're talking about so I see a greater than equal. See a greater than equal. I see this is just signed and unsigned, and this is less than. I don't know what you mean by n minus 1. So we're comparing two register values in all of these. So what do you mean by n minus 1? The short story is, you know, for something like optimizing an instruction set, you want to make it so that the compiler has enough flexibility to the comparison. No, I know what you mean by the comparison, but your example of branch if greater than n minus 1 versus branch if greater than or equal to n. So we want to include the entire set of numbers here. You can't access a constant here? No. So you can only access a constant, I think, in the unconditional branches, which are the jump and link register. So this is saying, yeah, this is using some relative PC. So this is basically saying x equals 1 is equal to PC plus 4. We want to go to PC plus 100, so plus this offset. And then for this link register, we're doing a procedure return with an indirect call. So yeah, our unconditional branches are the only thing that have immediate inputs. All of these comparison ones, because if you think about it, you know, if we start including immediates everywhere, it doesn't really make sense. So usually when we're doing comparisons, what are we comparing against? So 0 is a good thing to compare against. We want to compare if, say, the difference of two things is greater than 0 or less than 0. And so we already have 0 stored in a register. That's by default. X0, the 0 register, is always 0. So if we're comparing against 0, why would we need an immediate? Okay, let's not get caught up on that too much. We're not even using the instruction set yet. We can go over a paper that's about the design of instruction sets later. That's fairly interesting. Okay, so let's see. Operations of the computer. I lost my pointer. Oh, there it is. Okay. Operations of the computer. Okay. Hardware. Burks, Goldstein, and von Neumann, 1947. So we're talking about, this is just after von Neumann's published his famous paper on EDVAC, the first stored program computer. This is about 2 years later. There must certainly be instructions for performing the fundamental arithmetic operations. Yep, I think this is actually from that paper. I think it was officially published in 47. It was written and a first draft was released in 45. And if you want to watch that video, hey, look at that YouTube channel. It's already up there. Okay. So every computer must be able to perform arithmetic. The RISC-V assembly language has the notation of A, B, add A, B, C, which means add B plus C and store that in A. And we'll see why it has this kind of format. It basically means, it's basically for the reason that this is eventually going to be going to binary. We're going to have something called an opcode, which basically is a binary way of representing something like add. And then we're going to have designated spots and some probably 32-bit instruction. We're going to have space for the value of A, the value of B, the value of C. Or not the value per se. We're going to have a specific combination of bits that say this register represents X1, this register represents X2, this register represents X3. Okay. Yep, and this is exactly what we said. The sum of B and C is placed in A. The sum of B and, okay, and so the sum of B and C and D is now in A. Okay, so they're just going through a sequence of instructions. That's fine. I think we can skip over this. I think we understand this. And they're just saying that that's comments, which is a common C notation. Oh, listen, I've got a fun fact for you guys. So I had a friend yesterday that had a job interview for a software developer position. And he went into the interview and they gave him some problem to solve. And the guy didn't know anything about C or C++, even though it was for a C and C++ programming position. And so the guy that was interviewing didn't even know how to write comments in C or C++. But this same notation isn't this the same notation that Java has? How do you not know like the most common way to make comments? The most common symbols that are for comments. It's usually 2 slashes or /*. That's really confusing to me. And this is for, yeah, it's really confusing to me. And this was for like a software developer position interview. And it was a coding interview. Okay. All right. let's move on. Also in my statistics, yeah, because I mean everything was originally, or most things are built off of C and C++, and because of that, you know, why not just adopt the same? I mean, why make something new for comments? What's the point? Maybe, yeah, that's pretty likely. Maybe it was a grad student. You ever watch, or you ever look at code written by grad students? Don't. Listen, I got a program from a team that's at University of California, Riverside. Yeah, UCR. And I asked for their code from a paper they published because I wanted to kind of evaluate some of their results and maybe look into some research related to that. The only code, or the only comments that they had in their entire program, was for a malloc instruction. Basically when they're just allocating for an array. And I was just thinking to myself, yeah, that's the part I didn't understand. When you malloced for an array, I didn't understand how you would allocate data. Great. You know, the entire research part had 0 comments. And, you know, when you're using a bunch of, you know, when you're using a bunch of values that you just say, okay, so this value is going to be 16, and you just write 16 in there instead of assigning it to a variable. Also, all the variable names were A, B, C, X1, X2. They did not have meaningful names. Never let a grad student write code. Never do it. Listen, apparently grad students fall under the same principle of, if it was hard to write, it should be hard to read. Okay, enough ranting. Let's learn some more. Let's move on. Okay. So here's a good design principle that we want to focus on. And this is something that's true. This is something that's true across, you know, pretty much all engineering, and, you know, in a lot of cases, software too. So if we make something simple but still functional, then if we need to repeat that many times, it's very easy to do that. So an easy example is DRAM. So DRAM consists of one transistor plus one capacitor. Very simple. That's why we can have such dense memory with DRAM, because it's very simple. Now, if we were to take something like, so let's look up a DRAM circuit. Let me look that up. DRAM circuit. Okay. This is a good one. Look how simple this is. This is all a DRAM circuit is. We have a capacitor, we have a transistor. That's it. So we can make very dense memory using this. Now let's look up SRAM. So SRAM uses cross-coupled inverters. And so now we can see why SRAM is it takes up way more space. So this is SRAM. So SRAM has 1, 2, 3, 4 different transistors, and it also has, and then it also has 2 resistors here. Yeah, and so these 2 transistors and 2 transistors, these actually make up an inverter. So that's why I mean, but when I say cross-coupled inverters, my guy, what are those? Listen, this is SRAM. This is memory. This is your fast memory that you want. But look at this. Look at the size of this. So what would you rather do if you want to add a lot of memory? Do you want to have to find a way to string a bunch of these together? Probably not. But if you could just string a bunch of those very simple DRAM circuits together, you know, you're not going to get great performance. It's not going to be amazing performance, but it's going to be very easy. So that's important. So let's see. Compiling 2C assignment statements into RISC-V. Okay. So let's see. Let's see how easy this is. So we'll notice that this is very simple for basic arithmetic. So if we have simple C statements, such as, assuming these are already initialized, we have A equals B plus C and D equals A plus E. So we know for the first one it's going to be an add. And we know that the first thing that comes is where we're storing it. So if we don't consider registers, which is fine a lot of the times, we can just say, okay, we're going to store an A. And then what are we adding together? We're adding B and C, which is what they have down here. And the same thing goes for the subtraction. So for subtraction, we can just say D, that's where we're storing, A, E. Now you may be asking yourself, oh, you know, what about the ordering, right? For subtraction. Does the ordering matter? No, I don't think it does, because a subtraction is just addition in binary. So if you represent signed numbers in binary, and you do something like, if you want to subtract, say, so we'll go into number systems later, but you'll just have to believe me on this. So this number right here is -1 in decimal. And this number here in binary is 1. Okay? So if we were to add these numbers together, this is going to be 0. We're going to carry a 1. This is going to be 0. We're going to carry a 1. This is going to be 0. We're going to carry a 1. And then this is going to be 0. We have a 1 out here, but we're only storing 4 bits, so this 1 actually disappears. We just discard it. So we see that -1 plus 1 is equal to 0. So it doesn't matter the order, because addition inside of the computer just looks like, or sorry, subtraction in the computer just looks like addition. So there's that quick answer. Ah, okay. So what about if we get something more complicated? So this is where we start to see why you should thank your friends that work on compilers. So what if we have some statement that works on this? Now, a compiler can't do all of this immediately. Let's see. So why are there two different operations for add and subtract? That's a good question. Let's look back at the instruction set. That might give us some answer. So let's look at the add subtract. So, okay. So this is for the subtract. So these are going to have to be signed. So x6 minus x7. So this is actually an interesting question here. So if we want to a minus e, we have a minus e, right? Okay, so that's the reason why we have subtract. It's because e itself is not a negative number. It's a positive number. In this scenario, we're looking at two numbers that are already, one's positive and one's negative. Here, a is positive and e is positive. So what happens in the computer when you do a subtraction, this is going to change a select line on the ALU, and we'll go over what that means. But basically what happens is when we do subtract, we take A, and let's say we have a box over here that does addition. We take A, we just feed it to this box. And so this is going to be our output. We take B, and so what happens here is B actually, let's just say it goes into this box. And this box is going to be plus or minus. And so some magical control signal is going to come from out here. Based upon what this instruction is, it's going to come into this box and it's going to say, is this going to be a positive B or a negative B? But the overall operation inside the machine is still just addition. But we have this box right here on B that basically says, okay, are we going to take B and turn it positive, or just pass it through as positive, or are we going to take B, turn it negative, and pass it through? So that's what we mean. That's what we mean by this over here, where subtraction is really just addition of negative numbers. Does that make sense, BP? That's why we need a different add and a subtract. It's because we need to convert B into a negative number and then add it. Okay, good. So let's go into something a little bit more interesting, which is if we have something like a complex expression. This isn't terribly complex, but we see that the order matters then, right? Yeah, correct. So whatever the second, whatever this is, right here, whatever this second in this assembly instruction, that's the letter that's going to be down here. So if this was, so let me write it the way that it was actually written. So this is going to be E. But, if instead it was, switch them around, if this was E and this was A, well then up here would be E and down here would be A. Okay. Yep. Perfect. That's exactly what happens in a computer. So let's go on. So what do you have? So we have this more complex expression, and we notice that our instruction set can't handle this. We don't have an instruction that has the ability to do addition and subtraction and also has 4 inputs as well. I wouldn't be surprised if x86 has something that could do this, though. We'll look at x86 later, but x86 has just super complicated instructions because it's a complex instruction set architecture known as a CISC architecture. So CISC versus RISC, which is a reduced instruction set. Okay. So how do we do this? So in the end of the day, we just have to split things up into temporary. So if I were to do this, I would say, okay, so let's have T0, and we're going to have that as what we're assigning to. And so let's do an add. Into T0, we're going to put G and H. Let me make that a little more clear. Then I want to calculate this, so I'll have another add. And I'll call this T1. And I'll add I and J. And then finally, I want to assign something to F that's the difference of these two. So I'm going to do sub T0, oh sorry, I want to store into F, so it's going to be sub F T0 T1. So all we really need to do, and what the compiler needs to do, is the compiler needs to be smart enough to know how to break something like this up into these fundamental instructions. And that's the job of the compiler. And the job of the compiler is to try to do this as efficiently as possible, meaning in the fewest number of instructions. Okay, check yourself. For a given function, which programming language likely takes the most lines of code? Put the three representations below in order. So what do you guys think? So we have 1, 2, 3. Just show me in order which you think takes the most lines of code. I'm going to say it's going to be 2 followed by 1 followed by 3. Oh, sorry, wait. Most lines of code. Yeah, sorry. RISC is always going to be first, then it's going to be 2. I would say it's 3, 2, 1, yeah. Because RISC is, of course, an assembly language, so you have to break everything down into these tiny little instructions. Then C's more low level than Java is because Java runs in this virtual environment, and then yeah. And then you have Java. I took a single course in Java. It was okay. I built a little ping pong game. Or like brick breaker game or something. It was okay. So some elaboration. So Java was envisioned by relying on software interpreter. Yeah, so it uses interpreter. And so it uses something called bytecode, which is different from RISC-V instruction set. And so it uses this in order to get close to C, because C runs on the you compile down C into the instruction set, while Java is an interpreted language. So it uses something called JIT, which is just-in-time compilation, and we'll see what that is later. But we won't go too into that. That's more on the software side. We care about architecture. We're architects. So let's see. We've got operands of the computer hardware. All right. So here we start to elaborate more on the instruction set and what that instruction set was actually defining. So unlike programs in high-level languages, the operands of arithmetic instructions are restricted. That means we can't put arbitrary numbers into our variables. Not like Python, where you can just shove it anything. What book is this? This book is Computer Organization and Design, RISC-V edition. So this is a book by, the authors are Patterson and Hennessy. So David Patterson and John Hennessy. Okay. So there's some special locations built directly into the hardware called registers. So these are those things that we're storing variables into. So registers are primitives used in hardware design that are also visible to the programmer. So if you're doing something in C, you can actually call assembly instructions directly. So the size of a register in RISC-V is 64 bits. Okay, it's a 64-bit. That's pretty good. So if we wanted to find the size of our register file, it's a pretty trivial exercise because we have 64 bits. And then it's going to be 64 bits times 32 registers per context, and then the number of contexts. Okay. The size of register in RISC-V, okay. So 64 bits is called a double word, and that's because usually in computer architecture, when we call something a word, we usually, that's a word is something that is usually 32 bits, so they're so clever they came up with another thing, which they just call it a double word. That's fine. So one major difference between the variables of a programming language and the registers is the limited number of registers, which is 32 on current computers, like RISC-V. So there's only 32 registers. Thus, continuing in our top-down stepwise evolution of the symbolic representation of RISC-V, we have added the restriction that the three operands of RISC-V arithmetic instructions must each be chosen from one of the 32 64-bit registers. Okay, that's fine. What book is, oh, yeah, so here. Computer Organization and Design, RISC 5, or RISC V. Okay, so this is the book. Now, I'm not going to tell you guys what to do, but I might Google Computer Organization and Design, RISC 5 PDF. And I'm not going to tell you what you can and cannot do. But if you want to look at maybe, you know, see if you like the book, you might be able to find something that maybe gives you one or two or all the chapters of the book. Maybe. But listen, I give you the Amazon link. I'm a good boy. Not buying the book before coming to class. Listen, hey guys, did you get your WebAssign codes? Did you guys get your PearsonSuccess.net codes? Exactly. That does sound illegal. That's why I gave you an Amazon link. Listen, I don't need to worry about stealing books. I have free access to all these books. Listen, it says 1665 pages, but that's because this is a mobile version of the book. So all the pages are smaller. This isn't like the PDF of the text before it was printed. This is the like Kindle type version of the book. So it's actually only about 700 pages. 800 max. They make the font bigger. They make it more mobile friendly. Okay, so let's move on. So, design principle number 2. Smaller is faster. Okay, so what do we mean by this? So we already know that DRAM is slower than SRAM. So what do we normally see DRAM and SRAM in? So when we generally build a design, or if we're doing multi-level marketing, we want to have tiers. And so we want to have a few people up here, or we want to have a very small type of structure up here that's very fast. This is the second level. We want to have something that's a little bit slower, but maybe has more capacity. And then we want all the schlubs to be down here at the very bottom. That, you know, this is the dregs that, you know, it just has to be here. All right. So this is generally, say, in a very conservative system, this is the L1, the L2, and this is main memory. So your L1 and L2, a lot of times these will be SRAM. But when you get to main memory, so we'll just call this MM, this is going to be DRAM, because we're concerned about capacity at this point. Even sometimes only the L1 will be SRAM. And so that's what we mean by this idea that smaller is faster. So your processor is up here. So right next to the processor, you want something really, really fast that can keep up with the processor. So you want something like SRAM. But if you're really, really far away and you're concerned more about your overall storage, you know, you put this giant DRAM cell that has like a, you know, 4 gig capacity, right? Versus these, which are on the K or megabyte capacity. So here's a fun fact. So they're talking about systems that only have 32 registers here. A fun fact for a GPU, every GPU thread has 256 registers, from register 0 to register 255. So there's your fun fact of the day about GPUs. Listen, I'm working on it, I'm trying to get us access to a pre-release GPU architecture book. That would be a lot of fun. I have the book, but I don't want to start presenting it on stream and get in trouble for it because I know the authors. Okay, so let's see. A very large number of registers may increase the clock cycle. So if we have a bigger structure, it's going to be slower. Okay. So that's fine. We can kind of skip a lot of this. Okay, so here we're going back to the same example that we did earlier, where f is equal to this g plus h minus I plus j. So instead, they redo this example, but this time, instead of using the variable names, they're using registers this time. So this is a fairly interesting concept. Yay, you did that. What did I do? Yeah, I did this. This time they're just using register names though. In the other example, they were using we used the just temporary variable names, but here they're actually, and so did they just use temporary variable names, but here they're doing the actual register mappings. But same idea, we don't need to spend any time on that. So memory operand. So now we've gone past arithmetic. Let's look at memory now. So programming languages have simple variables that contain single data elements, as in these examples, but they also have more complex data structures. So they have arrays and structures. And then these composite data structures contain many more data elements than there are registers in a computer. So if we only had registers 0 through 31, we can't store a lot of things there, so we need a bigger structure to do that. And so that's going to be our memory. And so that's referring to one of these 5 components, which is memory. And so here they're just kind of showing the scale. So you can only contain a small amount of data in registers, but you can store billions of data elements in memory, which is why the larger data structures, like arrays and structures, are kept in memory. Neat. So, as explained above, arithmetic operations occur only on registers. So when we want to do something arithmetic, we need to take something from memory and bring it into registers. And so that's why data transfer instructions exist. But memory, we can't address memory like we can registers. So with registers, we can just say, get me x2. But memory doesn't work that way. You can't say, get me, M8. We have to be a little more clever, and we have to use addresses this time. So memory is just a large single-dimensional array. And so all this means is we can address memory just like it's a giant array, kind of like we saw earlier, where we're basically doing mem 0, mem of 8. This is all we're doing. This is how we're going to be accessing things from memory. But there's instructions to do this for us, because this isn't the correct syntax that we would use. Okay, so let's move on. Here we go. Let's zoom out a little bit. So here we have data and very simple addresses, 0, 1, 2, 3. And then it stores 1, 101, 10, 100. So if you're interested, this is 1, this is 5, this is 2, this is 4. I don't know if this is signed or not. This is assuming unsigned. Unsigned numbers. So if we want to move something from memory to the processor, that's going to be a load instruction. So let's see. The format of the load instruction is the name of the operation, so LD, followed by the register to be loaded. So where are we going to put what we're taking from memory? And then a constant used to access memory. So this is going to be where we're getting the address. And so the sum of the constant portion of the instruction and the contents of the second register forms the memory address. So let's look at this example up here. So let's say we wanted to get this. We wanted to get what was stored at address 2. So that means, and let's say we had x1, and let's say that was equal to 1. So if we wanted to load something into x2, we want x2 equal to mem of 2. We would have to do something along the lines of load into x2 1 of x1. And so what 1 of x1 gets translated to is x1 plus 1, or 1 plus 1, which is 2. That makes sense? So this constant right here is just an offset. So if we have some value here, we can always just use an offset. Okay. So that way we can, the reason why we want something like x1 here, why we don't want to set x1 equal to 2 directly, is usually we want x1 to maybe equal 0. Because then that'll be like the start of an array. I didn't understand the offset. Okay. So let me get the eraser out. Oh, okay. Okay, you get it now? Yeah, basically, if you think of this data as an array, the offset is basically just your index. And then your register value is just going to be your base. So you can think of it as like base index, which I think is actually how it's defined. And so we already went through an example, so we can skip this one. Okay, so hardware-software interface. So this is a book that, it's called Computer Organization and Design, the hardware-software interface. So we want to talk about how software and hardware talk to each other. So let's see what they have to say here. In addition to associating variables with registers, the compiler allocates data structures like arrays to locations in memory. The compiler can then place the proper starting addresses into the data transfer instructions. Okay, so basically what they're saying here is that the compiler is going to manage memory for us. Since 8-bit bytes are useful in many programs, virtually all architectures today address individual bytes. Okay, so that's pretty clear. So we address individual bytes just because that's what the architectures generally do. So therefore, the address of a double word matches the address of one of the 8-bit bytes within the double word. Okay, and so we can actually let's see, what's a good way to, or the address of one of the 8 bytes within a double word. Yeah, that's right, because a byte is 8 bits. So like we said earlier, I'll call it just DW. So a double word is equal to 8 bytes, and a byte is equal to 8 bits. So a double word, oops, is equal to 8 bytes times 8 bits per byte, which is just going to mean a double word is 64 bits. Okay. That's fine. And so, yeah, therefore all the addresses of a double word matches the address of one of the 8 bytes within the double word, and addresses of sequential double words differ by 8. Okay, so this is basically just saying that if we want to address double words in order, we're not going to do something along the lines of mem 0, mem 1. Because it's 8 bytes away from each other, it's going to be mem 0, mem 8. Because mem 0 through 7 are the 8 bytes of mem 0. Okay. We can and we just prove that to ourselves. So that's what this is saying right here. The same thing. Okay. So computers divide into those that use the address of the leftmost or big end byte as the double word address versus those that use the rightmost or little end byte. RISC-V belongs to the latter camp, referred to as Little Endian. So I don't think this book has a diagram. So the Indianness can be kind of confusing. So let me look up a good diagram. Indian meaning, or Indian picture. Okay. So let's view this image. Okay. So basically what they're saying is that if we have these identical, so it just depends where the most significant bits are. So if we had two identical we had two identical sets of values, your highest address in Big Endian is going to refer to your they're basically reversed of one another as far as addressing goes. So in this one, this is the most significant bit. So if we were to turn this out, this number would be this number itself would be 1, 2, 3, 4, 5, 6, 7. And so the biggest bit here, or here, it's probably better if I just draw this. So basically, what this is saying is that if we have a number that's 0, 1, 2, 3, 4, 5, 6, 7, and say we have to break it up into little chunks of 2. If we do that, we can call this address say 0, 1, 2, 3 in ascending order. And so if we break this down as like a number system, or let's do something even more simple. Let's look at an example of 0, 1, 2, 3. If we break this down as a number system, this would be 0 times 10 to the 3 plus 1 times 10 to the 2 plus 2 times 10 to the 1 plus 3 times 10 to the 0. Okay, so that's this number. This number is equal to 123. Same thing. Now, all we're saying here is that let's say that each one of these bits has to be in a different address. So this has to be at address 0. This has to be at address 1. This has to be at address 2. This has to be at address 3. Now, this is how it works in Big Endian. The big end is the smallest address. Now, in Little Endian, it's just the opposite. So in Little Endian, it would be like this. So the largest, most significant bit would be at the largest address. So that's what we mean by Little Endian and Big Endian. If you don't understand, I completely get it. Little Endian and Big Endian is it's a very confusing concept to get. Okay, you got it. Okay. That's basically all they're saying. Most things are Big Endian, though. They're not Little Endian. Okay. So let's see. Let's get that highlighter tool back. Oh, sorry. Most are Little Endian, rather. I misspoke. Since the order matters only if you access the identical data, but okay, blah, 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 blah. Okay, this is boring. So this is just talking about alignment. So all that has to deal with is alignment. And so it should make sense why Little Endian makes more sense, right? It's because generally when we're thinking about numbers, we don't think about them in reverse. It's just a convention. It's not about performance. It's just personal preference. It's whatever the architect decided they wanted to do. There's probably some performance considerations that you can make, but I don't know what they would be. You could see why Little Endian makes more sense, though, because this is how we think about numbers. We think about the largest numbers being the farthest away from the smallest numbers as far as addresses go. So this makes the most sense based upon the number systems that we use day to day and that we work with. Okay. So let's see, elaboration. In many architectures, words must start at addresses that are multiples of 4, and double words must start at addresses that are multiples of 8. So this makes sense, because if we're loading in words, every word is going to be 32 bits. Yeah, the other way is less intuitive. I don't know why there's this decision. I mean, it's basically just, you know, it's two different ways to do the same thing. Okay, so I can give you an example where it makes sense to use Big Endian over Little Endian. Okay. I can give you an example where I think it makes sense. And that's in arithmetic. And if we're able to do arithmetic directly on memory addresses. So, if we're going to compare two numbers in arithmetic, if we're going to compare two numbers in a computer, so think about how we would do that. So 1, 0, 1 versus 0, 1, 1. So this is 5 and this is 3. So how would we compare these two numbers? Well, one way we could do it is we could go, okay, are these numbers the same? Yeah, okay, so let's check the next bit. Are these numbers the same? No, but we still have more numbers to check. So let's look here. Are these numbers the same? Nope. So 5 must be the bigger number. Now, think about this in terms of addresses. So in Big Endian, this would be 0, 1, 2. And Little Endian, this would be 2, 1, 0. So this is address. So this is big address, this is little address. So when we compare two numbers, generally we compare them the opposite way. We want to check the biggest digit first, because then from this first digit we can say, okay, this one will, this is bigger, guaranteed. It's always bigger. So does that make sense? So if we're able to, if we're doing something where we're comparing directly based upon addresses, it's easier to count from 0 to 1 to 2 than it would be to initialize from some variable up here 2 and then subtract down to 1 to 0. So that's my intuition on an argument you could make for using a different type of a different Indianness. Okay. Okay. So let's keep going. So let's look at what they mean by alignment restriction. So in many architectures, words must start at addresses that are multiples of 4. That makes sense. Listen, that's not Indians with an I. That's Indians with an E. You know, we gotta be careful there. Indian, E-N-D. This okay, so the requirement where everything has to be stored in multiples of 4 or multiples of 8 is it's a common, this is based upon the physical architecture. So imagine if we had an array, right? That was here. So let's split it up, and let's say that each of these are 4 bytes. Now, think about it this way. So if we were to store things in multiples of 4, then this would be 0, this would be 1, this would be 2, this would be 3. Makes sense. Let's see. I mean, that could make for faster comparisons if the most significant bits are often different from one another in those comparisons. No, but that's the wrong way to look at it, because it's not a matter of the first bits being different from one another in those comparisons. If you're doing any comparison, if you start from the least significant bit, you have to check every single bit. If you start from the most significant bit, you only have to check until there's a difference. So that's the idea. That's the cost difference. So if we go back to this example that we were working on, so if we store things in terms of this alignment where things can only be every 4 bytes or 8 bytes. Yeah, that's right. That's exactly what I just said. And that's what we did in this example. We check these two. Okay, they're the same, so we'll check the next. We check these two, they're different, but that doesn't mean anything. That means that we just have to continue to the next and see if they're different. Yeah. So think of it. So you can think of it. We'll run through this example again really quickly. So 1 0 1 0 1 1. So if you ignore these and are just comparing the first two numbers, it looks like you're comparing 1 and 1. Okay. So they're the same. So we need to look at the next bit. So let's add a bit back. And we have 0 and 1. So now it looks like we're comparing 1 and 3. Okay. So 3 is definitely bigger, but there's still some unknowns over here. So this result doesn't mean anything. Because when we add the final bits back, 1 and 0, this turns to 5, this stays at 3. So this intermediate result of comparing these didn't mean anything. This was an absolutely useless comparison, because it didn't give us any information that allowed us to return to a conclusion. We had to go to the next set of bits anyway. I don't know. I don't know if you can make an argument. You can't make an argument that going from the least significant bit is ever better than the most significant bit. Okay, so let's get back to this example that we were working on. So let's just see here how this is going to work. So if we have an array, And, oh, no problem. Listen, this entire stream, you don't need to say sorry for the derailment. This entire stream is to clear up every single one of those little details that might be confusing. That's the point of this. This teaching stream is only to create the best computer architects. The people that know the most foundational information about computer architecture and can reason about computer architecture. That's the point. Okay. So, if we go to this example again, where we have, if each of these blocks represents a byte, we can either store if each of these is 4 bytes, then we can either store 4 words or 2 double words. Which makes sense, because if this is 4, if this is 4, if this is 4, if this is 4, that means we have 16 total bytes. So this is 16 bytes. And so we can either store 2 words, or double words, because these are 8 bytes, or 4 words, because these are 4 bytes each. Now, let's see why alignment matters. So why does alignment matter? It's because if we didn't use alignment, that means we could do something like this. So let's consider a single chunk of those 4 bytes, right? So now each of these is 1 byte. So it's the size of 8 bits. It's the size of one word. And let's put one more on here, right? So if we allowed things not to be multiples of 4, that means when we stored something, we could potentially wind up with something like this. We could potentially wind up with this blue being a word being stored. But what about this guy at the very end? This guy's unusable now. You can't store a word here because it's not a continuous region of memory. So that's why we have to worry about alignment. It's because we wind up with these situations where we don't want these little fragments of memory that are unusable. And so if you guys remember, listen, guys, if you remember the old days, remember on old PCs when you would have to defrag your computer, right? You'd have to defrag your memory. You'd have to run like your disk defragmenter. Yeah, so do you know what that was doing? So here's what that was doing. You basically had memory. Oops, that's not a good line. You had this big memory space. And this was cut up into a bunch of sections. And so what would happen is an application would come in and say, okay, I need this amount. And then another application would say, okay, well, I need maybe this amount. But look, we have these 3 stragglers here, right? Now, unless we have some tiny application that only uses one of these, then, you know, how are we going to store another application here? So when you run a disk defragmenter, what happens in the old days when this was still relevant, it starts moving all of these sectors around. And so you wind up with something like this. So all of your applications move up here, and it groups those stragglers down here into one continuous region so another application could use it. Yeah, I mean, this is why that defragging felt so good back in the day. This is what it was doing physically. Physically, it was moving this memory around so that you could have more contiguous memory space. Why can't apps store memory in non-contiguous continuous regions? Okay, so in some systems you can. In some systems you can, but think about the overhead that's relied upon that. So what do you have to do as far as when you're trying to access different regions of memory? You're going to have to look up different spots in memory for different regions of your app. So that sounds like a performance overhead. And that doesn't sound great. If it's all together, you don't have to do that searching. And like I said, there are systems that allow you to break up large contiguous regions of memory into smaller ones. Okay. But Flash? So there's no such thing as defragmenting on Flash. There's no such thing as defragmenting anymore. Yeah, that's why you can't run like the Windows defragmenter. It doesn't exist. This was purely that's why I was talking about back in the day. Yeah. No, it's an interesting thing. We can go into that sometime. So when I do the operating systems course, this is actually a specific topic in the course because this is something that's tied in with the operating system. So yeah, we'll go into that in the operating systems course. So stick around sometime and we'll go into that. Okay. So let's see what they do here. So here they're going to give an example. Let's see. I don't know if you missed the question. Without alignment restrictions, could you also overwrite half a word, for instance? No. No, it's going to be smart enough. So if you didn't have the... So this is, of course, in a theoretical scenario. So if you didn't have alignment restrictions, that means you would have to prevent that in the architecture. You can prevent, overwriting something in the architecture like that. However, you can't prevent the little regions of memory so what would happen? You would have to build some system where if you tried to write into the starting address of that didn't have enough continuous part of memory, what would happen is it would have to check to see if there's sufficient continuous memory at that location. I mean, so BP, you can think about this for double words, right? So what happens? It says I can store words in double words. So if I can store double words, what if I stored a double word 4 bytes in a smaller address than a word? So it would seem like I would overwrite that, right? But so there has to be some kind of checking mechanism to make sure that when you write a double word, you're not overwriting some other address. Does that make sense? Okay. So let's continue on. So compiling using load and store. I don't like red. Not when I'm not on this. Okay. So now we're taking some C statement, this basic, we're assigning to some part of memory the addition of H and some other part of memory. Now, one thing we'll notice here is that this is where it comes into the importance of the compiler. Because just accessing A of 8, this is something that has to be done in its own instruction. In x86, this is actually legal. In x86, you can add a immediate or register to a location in memory and store that in memory. I think that's supported in x86, which you may be asking yourself, that seems really confusing. Why would they do that? And the answer is, it's Intel. They shouldn't have, but They did anyway. I don't know why. It's a good question. Ask them why they did that. That's why x86 is so hard to understand. Okay. So, let's see. Let's move forward. So what they have to do first is they have to load that value, a of 8, and they define that here of how they're getting this information. So this 64, this comes from the fact that they are loading, let's see, so they're double words, right? Yeah. So they need an address that's 64 bytes away, because let's see. Let me get out the pen. So let's break this down for a second. So a of 8, what does a of 8 mean? This means they want to access the 9th double word. And the reason why it's 9th is because you have 0 through 7. So you have 8 previous to it. And so in order to get there, you need to go past the first 8 double words. So 8 double words are each 8 bytes per double word. So this is going to be 64 bytes, right? And so that's why we have to have this offset down here of 64. Okay, and then we just do addition like we knew earlier. And then we have a store. And so this time we want to put it in 12. So if we put it in 12, just kind of we calculated earlier, we want to put it in the 13th double word location. So if we calculate that out, we want to do 13, so let's see. So 64 is 8. So it's going to, it's just going to be 64 plus 32 is 96. And so I was able to just figure this out quickly, because if 8 is equal to 64, and if I just break that down into, that means that 4 is equal to 32, 8 equals 64, that means 12 is 96. So I did that math in my head real quick. So that's why we have an offset of 96 right here. Okay, that's it. Simple. Fairly simple. See, here's the thing about computer architecture. It's all simple. It's just confusing. There's nothing extraordinarily complicated, but they make it confusing. Oh wow, I've been streaming for an hour and 40 minutes. I didn't realize it had been that long. That's okay. Listen, we're here to go through all of chapter 2. And I think we're getting fairly close. I think. Ooh, unless the book pages aren't aligned with the... Oh, it doesn't matter. I don't care. Okay, so hardware-software interface. So let's see if they have any interesting notes here on the hardware-software interface. So many programs have more variables than computers have registers. So so this is going to bring up an idea of register spilling. So if we try to use too many registers in a program, what happens is a process called spilling, where things that would normally be stored with registers are shipped off to memory. And this usually causes a higher overhead, because that means when we try to access something that we think is in a register, it actually has to go to memory, find it in memory, and then load it back. So this is just talking about data movement. Okay, so let's talk about energy for a second. So if we have 64-bit data, registers are very fast. They're 200 times faster and 10,000 times more energy efficient than DRAM. So 200 times faster than DRAM. Very, very fast. So that's why we have caches. So caches keep us from having to go to DRAM all the time, especially because it's 10,000x worse energy-wise for cache lines. So that's why we have caches, because caches keep us from having to go to DRAM all the time. It allows us to stay in like SRAM. Okay. Oh, and here's another thing. So we looked at memory earlier. We looked at memory last lecture. And does anyone remember, I don't know if anyone was here yesterday, but does anyone remember whether static or dynamic power was the biggest energy concern with DRAM? Does anyone remember? I'll give you a hint, they're close. And so dynamic power is the power that's associated with flipping bits. Static power is the power when the component is idle. Obviously, I wasn't there. That's okay. So the answer is actually dynamic power. So it takes more energy, kind of unsurprisingly, but not necessarily intuitively. It takes more energy to switch DRAM than it does for DRAM to just sit idle. But I think the split is 60-40. So 60% of the power of DRAM comes from switching, 40% comes from static power. Okay. So let's say so constants or immediate operand. Okay. So we're going to take a quick break here. I'm going to go get some water, and then I'll be back in just a second, and we'll go on to the other kinds of instruction sets, or the other parts of the instructions. And so we're getting some progress in here. I don't think we're as far along as I thought. I don't think those page numbers were accurate. But here, let me get some water, and I'll be right back. I'll catch you on YouTube. Okay. That works. Yeah, see you later, BP. All right. Let's see. I'm gonna do some more. I'm gonna do some. Let's get some advertising going. Listen, we got to grow the stream, man. We have to bring everyone into the computer architecture flock. That's the goal. That's the goal of this stream. The only goal of this stream. The goal of this stream isn't monetization. The goal of this stream isn't making a career. The goal of this stream, more computer architects. All of them. Everyone's a computer architect now. That's what's going on here. All right, let's move on. So we're looking at constant and immediate operands. So this should be fairly quick. So basically all that we mean when we're adding immediates or we're adding constants is that instead of specifying a register, we specify the value directly. So this is a fairly simple concept, and we can kind of skip over all this because all we're doing is we're just adding constants. So if we go ahead and move ahead, and we look at, here we have a couple things to keep in mind. So we notice that we generally want, that 0 is a very common number that we use. We compare against 0 a lot. We do a lot of operations with 0. So that's why we have, because we want to make the common case fast, that's why we have a dedicated 0 register. Oh, you just followed, so you, wait, option selects, are you leaving too? I'm sure it's late there. I'm sure it's like midnight or 1. Okay, let's move on. Oh, no, you'll stay. Okay. Okay, that's awesome. Well, hey, listen, if you like the content like option selects did, and he decided to follow the channel, listen, follow that channel, man. If you want more computer architecture and operating systems and compilers and logic design, even some math content, you know, check out the stream, guys. Check out the YouTube. You know, we got the links in the we got the links below the stream right now to the YouTube and to the Twitter. You can press whatever that isn't, like a bell or something, to follow the channel. Listen, if you want more content like this, hey, just give me a follow. Okay, so let's check ourselves before we wreck ourselves. So given the importance of registers, what is the rate of increase in the number of registers of a chip over time? So, okay, so this is just some more information. So they increase as fast as Moore's law, which predicts doubling, or very slow. Since programmers usually distributed in the language of the computer, there is inertia in instruction set architecture, so the number of registers increase only as fast as the new instruction sets become viable. Okay. So what do you guys think? Do you think that the number of instructions or the number of registers on a chip, how do you think that scales over time? Do you think that that goes very quickly or very slowly? You can just say like fast or slow, and then I'll tell you what the answer is. 2, very slow. All right, so the answer is absolutely very slow. Oh, well, thanks for supporting me. Okay, yeah, the answer is absolutely very slow. And so the reason for that is, think about the difference between creating a new instruction set architecture every single time a new generation comes out. So that means every 2 years, right? So every 2 years or 18 months, you're making a new ISA. Let's look at Intel. What does Intel use? Intel uses x86, right? Now here's a better question. How long has Intel used the x86 architecture? They've used the x86 architecture a very long time. So, you know, that's the reason why the number of registers, they don't scale like Moore's law. It's because, you know, Intel still uses x86, so they're not just throwing registers in there, because that means you need to change the whole ISA, and they don't really change ISAs that frequently because that's hard, because that breaks every program. Okay, so let's see. So, any interesting information here? Nope. Nothing too particularly interesting. So, migration from 32-bit address computers to 64-bit. Okay. So this is interesting. So, we moved a while ago to 64-bit machines. But one of the things to keep in mind is that when we have a 64-bit machine, we don't necessarily use all 64 bits for an address range? Okay, question. When you say that breaks every program, what do you mean by that? Do you have a simple example? Sure. So if you fundamentally change the way that programs are stored in the machine, that means that it's going to break the compilers, right? So compilers are optimized to understand the resource what resources that a computer has. And when you change the number of registers, you have to keep in mind, you're not just changing the number of registers in a machine. You have to change every single control unit that deals with those registers, because now they need to know, okay, which registers can I access? Well, I can access this larger range of registers, so I need a larger storage unit in order to store more bits for addressing these different registers. Maybe I can support different sizes of data now in these registers. So what I mean by this breaks every program is that compilers no longer work, because compilers no longer understand what the underlying architecture is. And so you would have to update all of your compilers to what the new ISA does. And then you have to update not only all your compilers, but sometimes if you have to keep in mind that programs can use inline assembly instructions. So that means that if you have a C program, you can actually, yeah, that would be, I agree. So if you have a C program, you can actually include assembly instructions in the C program. That way you're guaranteed that they show up in the compiled result. And so because of all these things, it makes it very, very difficult. So ISAs change very, very slowly. ISA being instruction set architecture. Okay. So here's another little fun fact about 64-bit machines, since we're talking about 64-bit machines. So in a 32-bit machine, you have an address space that is 2 to the 32. Right? A virtual address space that's 2 to the 32. So this is 1K, 1 meg, 1 gig, 2 gigs. This is a 4 gigabyte virtual address space. So now we have, so this is for a 32-bit machine. For a 32-bit machine, we have 2 to the 32. So we have 4 gig of memory, right? So the question is, what do we have for a 64-bit machine? Can you take a guess? Take a guess. Take a wild guess of what the range is we have for a 64-bit machine. So keep in mind that for a 32-bit, we have 2 to the 32. So what do we have for a 64-bit machine? We have 2 to the, so it's going to be, I think it's 2 to the 48, or is it 54? Or it's like 50, oh, it's I think it's 2 to the 52. Because if you think of what 2 to the 64 is, 2 to the 64 is a really big number. So 10 is K, 20 is meg, 30 is gig, 40 is terabyte, 50 is petabyte, 60 is yottabyte. So this is going to be, let's see, so this is going to be 64, so it's going to be 1, then it's going to be 2, 4, 8. So that would give us 16 yottabytes of an address range. No one needs that. No one needs that, so they limit it to like 2 to the 52 or 2 to the 54. So that's just a fun little example of 32-bit versus 64-bit machines. So it's reasonable for 32-bit machines because that's only 4 gigs. But 64-bit machines, you're getting into like having 16 yottabytes. That's a lot of data. Okay, so now we get to look at signed and unsigned numbers for a little bit and kind of understand this. If you caught my computer arithmetic stream, we went over a lot of this, so I'll try to be brief. I don't do a good job at being brief, but I probably should work on that. So, let's see. So, for 123, base 10 is equal to 1111011. And so, the way that you can prove this to yourself is, let's just expand this out. So this is 1, 2, 3, 4, 5, 6. So this is just going to be 1 times 10 to the 6, or sorry, whoops, 1 times 2 to the 6 plus 1 times 2 to the 7, or 5th, plus 1 times 2 to the 4th, plus 1 times 2 to the 3rd, plus 0, plus 1 times 2 to the 1, plus 1 times 2 to the 0. And so this is the same thing as that 1111011. And so we can just kind of expand this out. So this is going to be 1 plus 2 plus 0 plus 8 plus 16 plus 32 plus 64. So this is going to be 64 plus 32 is 96, plus 16 is going to be 112. So plus 16 is going to equal 112. Yeah. Right? Yeah. Plus 8 is going to equal 120, plus 2 is equal to 122, plus 1 is equal to 123. So that's how you can go back and forth. So you can convert from decimal to binary, and it's fairly easy. For doing that, let's just look at something like 12. So so the way that you do this is you just divide by 2. So you divide 12 by 2 is 6, and you check the remainder. So you do 12 divided by 2. Let's make a little table. So let's have the equation here, let's have the remainder here, and let's have a digit here. So let's do 12 divided by 2. The remainder for this is 0, and then the digit here is going to be 0. Then look at the next one. We're going to have 6. So we're going to have 6 divided by 2. That's going to be 0 remainder, and our digit's going to be 0. Then we're going to have 3 divided by 2, and that's going to have a remainder of 1, and so we're going to have a digit of 1. And then we're going to have 1 left over here, which is smaller than 2, so that's already a remainder of 1 and a digit of 1. Now we kind of zip this up, and so our binary number is this number right here, which is 1100. So this is 8 plus 4 is 12. Okay. So that's how you kind of go back and forth between binary and decimal. That's just for a little bit of context. Okay, so let's move on. So, okay, so this is the, I think we can skip most of this now because we've gone over this. Yep. Yep, yeah, we can skip actually all of this now because we already did this kind of conversion. And then we already talked about, so let's talk a little bit about negative numbers. So for negative numbers, if we have a number like 0, 1, 1, which is equal to 3. And we know this because this is 0 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0. So this is just equal to 2 plus 1 is equal to 3. Okay, so if we wanted the negative version of this, we can do something called 2's complement. And that's where we flip all the bits. So step 1, flip. So 0, 1, 1 goes to 1, 0, 0. Now, the next part is we add 1. So we add 1 to this, and we get 1, 0, 1. And what this does to our number system now is instead of being for n different digits, instead of having 1 times 2 to the n minus 1 plus 1 times 2, or sorry, this is just going to be some constant c n minus 1 times 2 to the n minus 1 plus c n minus 2 c or times 2 to the n minus 2 all the way to c, oh sorry, what's a good way to write this? Basically, your most significant bit now, so instead of having our original number system, which was 2 to the 1 times 2 to the, or I'm messing up right here. Okay, so 0 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0. So we see it's just ascending powers of 2. So in our new number system, the first digit here is going to be negative, and that's what happens when we do these two processes. When we flip and then we add 1, we change the number system to look like this now. And then we can calculate from here. So this is going to be negative 1 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0. And this is going to be negative 4 plus 1 is equal to negative 3. So we see we started with 3 and now we have negative 3. So that's just how 2's complement works. That was a little confusing because I got distracted, but that's the overall idea. This is not going to be very, if you're just trying to get a comprehensive understanding of computer architecture, this won't kill you if you don't get this right away. All right. So the main summary is that we need to represent both positive and negative numbers. Yep. Okay. There's actually an interesting talk I heard, and it deals with how computers represent floating point numbers. And it was a guy from, he's an expatriate from the United States that now is a professor at a university in Singapore, and he's like he's a brilliant electrical engineer that lives in Singapore and teaches there, and he's like an IEEE fellow, and he came up with his own standard for floating point representation, and it's what is it? I just watched a talk from him yesterday. Let me post that talk in chat because I found it really interesting. It was from Stanford. The talk was. Let me find it from yesterday. Yeah, it's not Noose or something or NUS. It's not. It's something similar to that though. It should be. So I watched it. I watched something from Donald Knuth as well. He's a great guy. Okay, here we go. Here we go. It's yeah, this John guy, John something. Okay. It's yeah, John Gustafson. And what is his for what it's called. Here's the lecture. It's very interesting. I enjoyed it. Let me just look up John Gustafson. Okay, here's his website. His work on publication links. Yeah, this is the guy. Dr. John L. Gustafson. What is he most known for? Oh, Unum. That's what it is. Unum computing. Yeah. Unum computing. The end of error. Unum computing. Yeah. That's what it is. It's pretty interesting. Oh, news. Okay, National University of Singapore. Yeah. Okay. Yep. Yeah. Yeah. I thought you were trying to say whatever that idea was. It's very interesting because there's pretty much like an infinite amount of representations for not a number in IEEE 754 standard, but in his you only have like 2. Okay. So we can skip this because we're talking about one's complement. No one uses one's complement. So now let's get to something more interesting than what we've talked about recently, which is representing instructions in the computer. So, we talked about instructions. We've talked about, assembly language. But, you can't give a computer words. You can't give a computer words and expect it to understand what you're talking about. You have to give it binary numbers. And so now we're going to get into how those are represented. So let's see what we have here. So let's do the next step, a refinement of the RISC-V language as an example. We'll show real RISC-V language version of an instruction. So let's have an add instruction. So what they're saying is this instruction right here is going to translate into these different binary, or these different decimal numbers, and then these will be represented by binary numbers later. And so each of these represents a specific field. So the first, fourth, and sixth fields tell the computer that the instruction performs addition. So that means this one, this one, and this one. I had to think if I was indexing by 0. So these 3 are purely related to setting up the control of the processor in order to understand that this instruction that we want is add. 21, 20, and 9 are the registers that we're using. So X9, 9 here, X20, X20, X21, X21. So we see that there's this direct mapping, and then what we're going to do is that this is eventually going to translate to binary. And so here we go. So this is exactly the instruction format and how it would look, at least for a add instruction. For an arithmetic instruction like this, or an ALU based instruction, so anything dealing with arithmetic, we're going to have, so this is going to be, let's see, this is 16 plus 5, so this is going to be x21. This is going to be 16 plus 4. This is going to be x20. And this is going to be 8 plus 1, x9. So there's our registers. So moving on. So we're going to refer to this, whenever we talk about binary, we're just going to call it machine language for simplicity's sake, or machine code. That way we don't get confused. Now usually when we print out something in a computer, we want it to be readable, even if it is binary. So that's why we invented hexadecimal. So hexadecimal is base 16, and basically what happens is we take these 4-bit chunks. So let's say we have 0, 1, 1, 0, 1, 1, 1, 1. And let's say these are together, right? So let's make them closer. So this is just a single string of binary digits. So 1, 1, 1, 1. So what we do is we define hexadecimal to be represented by 0 through 9, and also A through F. So we have 16 different digits or letters here total to represent all 16 possibilities for each digit. So here we can just break them up, and what we find is that, so this number by itself is 16, or sorry, is 15. So this is going to be F. And then this number, we can just, it's going to be 0 plus 2 plus 4. So this is 6. So in hexadecimal, this would be 0x6f. Okay. So we have a more condensed way to write binary, which is convenient because unlike decimal, this is a this is done in powers of 2 instead of decimal. Which is powers of 10. Yep, numbers in base 16, hex. And so here they have an example that kind of shows that. So each hexadecimal digit maps to 4 binary digits, and the reverse is true. Interesting. Okay, so let's see here. So let's actually look at what the fields represent. So we see that here's are going to be our register. So RD just stands for register destination, or our destination register. RS1 and RS2 are going to be our 2 source registers. That's going to be our inputs to our mathematical operation. Then we have these 3, which are more interesting. So funct3, funct7, and opcode. So we have funct3 and funct7. So these are just opcode fields. So these are just going to be predefined by the architecture to do some kind of control based on how they're set. And so opcode is going to tell what instruction it is. So the basic operation of this instruction. So it's all the 7 bits in here are going to be used to say, okay, is this an add? Is this a subtract? Is this a load? And so the funct3 and funct7 are just if we need additional bits for opcode. Because there's an interesting thing where, so when we talk about microcode, generally there's some space left to define custom instructions in processors. So we want this flexibility with our opcodes in order to say, you know, if we have a special instruction we want to implement, we want to have enough opcode space to implement it, and then we can just write the microcode and load it on our processor, and then we have our own instruction. Okay, so here's a good design principle that we should focus on for a second, and that's design principle 3. Good design demands good compromises. So like we've mentioned many times before, we can't have the best performance and the best power. It's never going to happen. Those two things fight each other every step of the way. Okay, so Generally, you have different types of instructions. So we have R-type instructions. Those are generally instructions that you use only registers. You have I-type instructions, which are instructions where you have an immediate operand. So you have, say, you're adding x2 plus 20 or plus 35 or 33. So like add I, that's an example. Then you also have load store instructions, and I forgot what they call those. S-type. Those are going to be S-type instructions. Yeah, so we break these down into 3 different instruction classes, being R-type, I-type, and S-type. R being register only, I-type being immediate, and then S-type being dealing with memory. Okay. So that's interesting. So let's move on. So here we just have a couple examples, but I think we get the idea, and we can move on. Okay. So let's look a little bit on what they're talking about, the hardware-software interface in this. So the desire to keep all instructions the same size conflicts with the desire to have as many registers as possible. Any increase in the number of registers use up at least one more bit in every register field of the instruction format. Given these constraints and the design principle, that smaller is faster, most instruction sets today have 16 or 32 general purpose registers. So yeah, that's an important thing. So if every single instruction that we're executing, if there's suddenly one more instruction to be represented, that means that, you know, all of these fields, so thousands upon thousands upon thousands of fields would need a single extra bit. And while that seems like, oh, it's only 1 bit, it's 1 bit times how many storage objects need that extra 1 bit, which is, it turns out to be a lot. Okay, so let's look at the big picture for a second. So as we know from our previous talks, today's computers are built on 2 things: that instructions are represented as numbers, so as binary digits, and that programs are stored in memory to be read or written just like data. So we have program memory and we have data memory. So we have these very simple concepts, and this is really all we need to keep in mind, are these simple concepts when we're talking about computer architecture. So when we're thinking about instructions, we don't want to get too bogged down in the weeds of, okay, well, what's the exact binary mapping of this load instruction or this store instruction? We can think of it as, okay, we have load instructions, we have store instructions. How does memory work? Okay, well, we know we're going to address memory, and we know that memory is aligned. And then we know that we need instructions to take things from memory and put things in memory. So it's really important that we try to make something like computer architecture, we want to make it as approachable as possible as far as it being reasonable. We don't want to make saying things too terribly confusing. Okay. So here we have a quick example of a stored program concept. So we'll have multiple programs, but then for those programs, we'll also have data. And these are stored together. And this is kind of the basis of what von Neumann architecture is. So basically, we have an accounting program that has payroll data in the same memory as it, and the same memory space that is, when I say memory space, I mean the entire scope of memory. They're together. Okay. So let's move on to, we'll briefly go over logical operations, but I don't think this will be too confusing for most people. So although first computers operated on full words, it became clear it was useful to operate on fields of bits within a word. So sometimes we only want to change certain parts of the data that we're working on. And so we can do this using our shifts and then our logical operations like OR and XOR and NOT. So it turns out that C and Java use the same as RISC-V. Okay. So the first thing we have are shifts. So in the case of a shift to the left, which would be a logical shift, we see that we just move these bits over by 4. So this guy goes 1, 2, 3, 4. Makes sense, right? But this happens to every single one of those bits. And then you may be asking, what happens to the bits at the end? So these guys, they just fall off. They disappear. Now, and then we wind up with 144. And we can see that because if we do 9 times 2 to the 4, which is 16, so 9 times 16, this is 144. I think that's correct. So let's do it real quick. 54, 5, 9, 9 plus 4, 14. Yep. And so shift right works the same way. It'll just shift to the right this time. Now and is exactly like we saw earlier. We just check to see if the two bits are the same, and if they are the same, they are that bit. If they're not, it's 0. So if we have 1, 1, 0 and 0, 1, 1, or let's do 0, 1, 0. So 0 and 0, they're the same, so 0. They're both 0. 1 and 1, they're both 1, so 1. 1 and 0, they're different, so 0. Pretty simple. Or we can think of it the same way, in the same context, that is. So if we have 1, 0, 1 and 0, 1, let's change this to a 0. So this time, it just checks to see if there is any 1, not that there's two 1s. So 0 or 0. Okay, so it's 0. Now 0 or 1, so it's 1 because we have at least a single 1 here. And then 1 or 0, it's 1. And if we had something like 1 or 1, it would just be 1 as well. Not, we'll just do the inverse. So if we do not 1, it becomes 0. And if we do not 0, it becomes 1. Then if we move down again to XOR, XOR we can kind of think of as it determines if there's an odd amount of 1s. So it's an exclusive OR. So if we have something like 1 and 1, so this is not exclusive, it's 0. If we have 1, 0, it is exclusive, so it's 1. And if we have 0, 0, there's no 1s here to begin with, so it's 0. And the reverse is true for this one. So 1, 0 or 0, 1 both give you 1. Okay. So we were able to get through that section pretty quickly because that's fairly intuitive. So 2.7. Instructions for making decisions. So what distinguishes a computer from a simple calculator is its ability to make decisions. So unlike a calculator that has a fixed program, this has the ability to change depending on what we need it to do. So decision making is commonly represented in programming language using the if statement, sometimes combined with go-to statements. So these will be things like loops and conditionals. These will determine where we go in a program. So the first instruction that we can look at that is part of these decision-making instructions is this BEQ, which stands for branch if equal. So all this is saying is that if RS1 is equal to RS2, then we go to whatever L1 points to. So L1 is just an arbitrary identifier. So we're just saying that L1 is some place that we want to go to. Okay. And then there's also B and E, which just stands for branch not equal. So if we just add an exclamation point here, we have the same thing as this instruction. And so these are called conditional branches. So that means it's a branch that we need to do some kind of calculation in order to go to some place like L1. So much for subtlety. I just joined. What are you explaining? So right now in this chapter, we're going over the instruction set, or what an instruction is in a computer, how we understand how instructions map to high-level languages, like how does addition in C, or subtraction in C, or addressing an array in C map to the actual instructions that are executed by the processor. And then right now specifically we're going over how do we jump around in a program. So if we have a for loop and we need to go back to the start of the for loop, how does the computer do that? So it does that with a thing called branches. So conditional branches, no problem. So conditional branches, like it defines down here, it tests a value, and then if that test passes, we go to a new address that we specify. Okay. So here we have a simple if-else statement, and let's see what that looks like in RISC-V code. So at the very top, we see that we need to first, if we were executing this code in C, what we'd expect as a programmer is our instruction gets to this if statement, and the first thing it does is it checks if I is equal to J, which is right here. And so there's two options. And so those two options are the next part, which is either f is equal to g plus h, or it assigns f equal to g minus h, and then it returns. So let's see how we would do that in an instruction. So here, what we do is we do a branch not equal. So we check, so x22 and x23 are I and j respectively. So we check if x22 is not equal to x23. So right now we're checking this condition, this I not equal to j. If it passes, we go to the else statement. If it fails, we need another instruction to go to, or we have to go to this statement next. And so we can write out, it's easier to see how this looks if we write this up together. So let's write this together. So let's do, we don't even need registers for this. Registers make this more confusing than it needs to be. So let's just write it within this box. So our first instruction is going to be branch not equal. We're going to compare I, j, and if it passes, we're going to go to else. Now, if it doesn't pass, it just continues executing the next instruction. So if this fails, that means this must pass, which means we can just automatically have add F, G, H here. And then down here we can have, let's see, how do they do it? Okay. So the way they have it is they have a go to, exit, and then they define else, which they define only as sub F, G, H, and then they have exit down here where they just return. So that's more or less how this assembly is going to look together. And so we can kind of see how they did it. They didn't do it together, which is kind of confusing. So first they do the branch, and if the branch passes, it goes to else. Then they execute the opposite path. If it doesn't go to else, then it branches. So they do a branch if equal x0 is equal to x0. So this will always be true. So this is basically a go to exit. Then they have a section of code for going to else. So this is where else goes to if it branches. And then finally we have an exit, and it'll do some kind of return down here. Okay, so loops work in the same way. So just like we saw right here, that we could branch from all the way up here in the program down to else, or we could branch to the exit of the program. We can also branch behind us. We can go to a previous address, and so that's how for loops work. So this is a simple while loop, and I wish they had a good example of a... So we can run through this code fairly quickly and understand how it works. So we define a loop. So this is going to be our while loop. And what we do here is we shift left logical by an immediate value. So we're just shifting something by an immediate value. So that's fine. We do some addition, we do some load, and then here we branch to the exit if we fail some test. Otherwise, down here we branch back to the loop. So basically what happens here is we spin in this loop or it's actually a little wider of a loop. We spin in this giant loop until we receive an exit down here at this branch equal to 0. Or no, sorry, if this branch not equal. If this branch not equal passes, we find our way out of the loop and we finish the program. Any questions on that? I think that should be fairly self-explanatory. So we can just ignore all of these instructions, and we can just care about these branching instructions for right now. So basically we have a loop up here. We do some stuff. We check to see if we finish the number of iterations we're supposed to do. If not, we continue on with the program and we go back to the top of the loop. If we're done with the number of iterations, we leave. Okay, so let's talk about basic blocks. So basic blocks is something that's important to understand. It's just a term that it's good to know. So such sequences of instructions that end in a branch are so fundamental to compiling that they are given their own buzzword, a basic block. So a basic block is a sequence of instructions without branches, except possibly at the end, and without branch targets or branch labels, except possibly at the beginning. One of the first early phases of compilation is breaking the program into basic blocks. So what we mean by this is, if we have it, you can think of it like in a C program or a Python program or a Java program, whatever language you use. You can think of this as a function. So a function satisfies these requirements because it doesn't have, so let's look back at the requirements. So there's no branch, there's no, so, you know, well, I suppose that's not really a great, well, no, never mind, I take that back. So when you compile a program, what happens is, a lot of times it will inline your functions to wherever you call them. So it'll just shove all the code for putting your function, or at least that's what it does with header files. Yeah, with header files, it'll just, wherever it's included, it just dumps the entire text of the, if you look at your intermediate compilation steps, it'll just dump all of your the contents of your header files wherever you do an include. So yeah, so this just basically says that what the first thing that a compiler does is it breaks your code up into bite-sized blocks that are all kind of independent of one another. So the little bite-sized blocks may bounce around from each other, but they don't bounce within themselves. So what I'm trying to say is, maybe it's better if I draw some circles. Circles are good. So if these are my basic blocks, they can go from one another in any arbitrary fashion that they want, but they don't bounce around within themselves. That's probably the better way to explain that. Okay. So these are just some stuff on testing. Branch greater than or equal to. Okay. So this is not entirely, that part was not entirely that interesting. So let's look at the bounds check shortcut. So treating signed numbers as if they were unsigned gives us a low-cost way of checking if 0 is less than or equal to x, which is less than y, which matches the index out of bounds check for arrays. The key is that negative integers in 2's complement notation look like large numbers in unsigned notation. And so we know this to be true because 1, 1, 1 in signed notation is equal to -1 in decimal, so base 10, this is base 2, while 0, 0, 1 in base 2 is equal to 1 in base 10. So that's what they mean by negative numbers look like very large numbers. Okay. So thus an unsigned comparison of x less than y checks if x is negative as well as if x is less than y. Okay. So this is just kind of a little optimization you can do. This isn't terribly interesting, but it's just it's exploiting some of the features of the binary representation for negative numbers in order to maybe speed up computation or reduce the number of instructions you need. So let's see how they do that. So use this shortcut to reduce an index out of bounds check. So they want to check if if register 20 is greater than or equal to register 11 if x of 20 is negative. So in that case, we just want to check, so if let's see, so branch greater than or equal to, so we want to check if x of 20 is greater than or equal to x of 11. Okay. And so let's try to come up with an example of how that actually works. So if we have 111 greater than or equal to 001. So let's see. Let's go over this again. I'm actually a little confused what they're talking about. So treating signed numbers as if they were unsigned gives us a low-cost way of checking if 0 is less than or equal to x, which is less than y, which matches the index out of bounds check for arrays. Okay. The key is that negative integers look okay. They look like large numbers. Thus, an unsigned comparison of x is less than y checks if f is x negative, as well as if x is less than y. Okay. But how does... So let's look at two negative numbers being compared. So if we take 111 and 101, and we do this comparison, if we check this condition, that means that this is a more negative number, so this is greater. So this is the comparison of two negative numbers. Okay, so that makes sense for the case of two negative numbers. Okay. And so this is saying that we can use that with positive numbers. Okay, never mind. I understand what they're saying here. I confused myself. So what they're saying is, they didn't make it clear here. So what they're saying is, this is the length of like an array. So we don't want to, so if we have an array that has 10 elements, right, which is going to be 0 through 9, it's going to help us if we want to check if we're accessing x of 50, or if we do x of -1, because these are both illegal. Okay, that makes more sense. Okay, so in this case, what happens if it checks if it's greater than or equal? If it's greater than or equal to some length like 8, or to some length like 3, which is 0, 1, 1, and say 0, 1, 1 is the bounds, that means we know that this number must be negative, because that the only way, this is a sign bit, so we know it must be negative, and we also know that it's illegal. Okay, so that was a little tangent, but I think it was important to understand that. Little optimizations. So that's the thing about programming in assembly. In assembly, you can do a lot of these tricky optimizations that don't necessarily, or they're not that straightforward. So most programming languages have a case or switch statement. So, you know, if you don't know what a case or a switch statement is, you can think of this as a different way of writing lots of if, else if, else if. It's a cleaner way. So the simplest way to implement switch is via a sequence of conditional tests, turning the switch statement into a chain of if, then, else statements. So that's exactly what I just said. Okay, and then sometimes the alternative may be more efficiently encoded as a table of addresses of alternative instruction sequences called a branch address table or a branch table, and the program needs only to index into that table and then branch to the appropriate sequence. So this is basically saying that we could do all the checks one after another, but if we had a way to just look up in some data structure which of the if, else statements I need to go to, it would be a lot faster. And so the way to do this is with indirect jumps. And so this is where we're jumping to a specific location, but we're jumping without some kind of condition. We're jumping just based upon, we're just jumping to an address that we give it. And so that's why it's called an unconditional branch. We don't need to test any conditions in order to branch. We can just jump. So this table of addresses that we're going to use in order to kind of jump around is called a branch table, like we said. And then, although there are many statements for decisions and loops in programming languages, the bedrock statement that implements them is just the conditional branch. So everything, whenever you write a program, it's important just to remember that all of these things will just at some point, at some layer, get broken down to just be branches. Okay, and we can skip over these. I think we understand the arithmetic. So let's talk a little bit about supporting procedures in computer hardware. So a procedure or function, so those are going to be interchangeable, is a tool to structure programs, both to make them easier to understand and to allow code to be reused. So if we're going to do something like add, if we always wanted to add two numbers together, or we always wanted to add, say, a number by, if we wanted to add, say, 8 numbers by some constant, we could write, just 8 different versions of something plus something plus something plus something. However, alternatively, we could just call a function that does that. And so that's what's going to be called a procedure. So procedures are one way to implement abstraction. So that means that instead of seeing the underlying details of what it's doing, we just call a function or procedure, depending on what you want to call it. Okay. So programs follow 6 steps during the execution of a procedure. So the first thing is we have to put parameters in a place where the procedure can access them. Then we have to hand off the reins of control to the procedure or the function. And then we have to acquire the storage resources needed for the procedure. That means if we need any memory or something. Then we perform the function. We put the result where the part of the function where we originally were can access it, and then we return control to where we came from. So 6 kind of fundamental ways we're going to use functions, or that functions can be defined. Okay, so let's talk a little bit about the jump and link. So in addition to allocating these registers, RISC-V assembly language includes an instruction just for procedures. It branches to an address and simultaneously slaves the address of the following instruction to the destination register RD. So this is a jump and link. Okay. So what happens is, unconditionally, so that means we just automatically we go to procedure address. But we save the spot that we're at in the program so that when we're done with the function, we know where to return to. So this is like when you write a C function and you write return, how does when you do a function call in C, how do we go to this little block of code that does something? How do we go there? How do we execute there? And then when we call return, how do we know to go where we came from? So that's using instructions like jump and link. And like we said, the return address is just, that's a link to where we came from. So the jump and link register instruction branches to the address stored in register X1, which is what we want to. Thus, the calling program, or caller, puts the parameter values in x10 to x17. Okay. So in this case, instead of using some identifier, this time we're explicitly saying x1 contains the address of where we want to go to. Or no, sorry, this is jump and link register. This isn't jump and link. So let's see what jump and link register does. So to support the return from procedure, we use jump and link register. The jump and link register function branches to the address stored in register x1. So we're still going to wherever this register has a value. And then it puts the parameter values in some predefined location called which are registers 10 through 17. And so we're just defining, different ways to name things. So caller and callee. I don't know. So this return, okay, so this is where, how if we return from something, usually it's like return 0. So that's what we're doing here. So we're always returning 0. So that's just going to be some condition that we predefine. So 0 probably means a good thing. That means we completed successfully. If some problem happens, you probably return a non-zero exit condition. Okay. So let's move along. So for historical reasons, the register is almost always called a program counter. So the program counter is a specific register that holds basically which instruction that we're currently on. So that's pretty simple. So let's talk about using more registers. So if a compiler needs more registers for a procedure than the 8 argument registers, then we have to find some other ways to do that. And so there's actually a data structure for doing such a thing, and that's the stack. And so what a stack is, it's a last in, first out queue. So basically how we can think of this, if we do a little drawing, is if we get a value, say x1, and we push this onto the stack, let's just say it lives, well, initially it's going to live at the very top of the stack. So this is going to be x1. Now say we want to add something new to the stack. Alright, option selects, have a nice night, man. Thanks for joining the stream. So say we want to have x2. So x2, what's going to happen is we're going to push another entry on. This top one is now going to be x2. This one is going to be x1 now. And if we were to do an operation such as we would pop something off the stack, so if you want to get something off, it's called a pop, and we want to put something on, it's called a push. If we pop something off, what's going to happen is the last thing that got put in, so in this case it was x2, comes off the stack. And so after we do a pop at this point, the only thing that's going to be on the stack is x1. Okay. Pretty simple. Pretty straightforward. So now we've defined what we mean by a stack. So let's see how this is going to work in reality. So remember, this only matters if we need more than the predefined argument registers, which in many cases is true. We will need more than that. So now let's work our way through this example. So let's look at the first instruction. So say we have 3 double words that we want to make space for on the stack. So what we're going to do is we first need to make space. So we take the stack pointer, which points to the top of the stack. So that's pointing to the top of the stack. Then the next thing we do is we decrement it by 24. So we move it down by 24. And the reason why it's 24 is because a double word is 8 bytes. So 8 bytes times 3 is 24. So 3 double words. Now that we've done this, we can start loading things on. So generally we do this in order. So what's on the bottom of the stack is going to be first. So first we're going to put whatever is supposed to be on the top of the stack. So this is going to be, so we're going to be storing x5 at the top. Then we're going to be storing x6 here at an offset of 8, and we're going to be storing 20 at an offset of 0. And the reason why this doesn't go to 24 right here is because, remember, each of these, x20, x6, x5, these are all double words. So x20 takes spot of 0 SP, stack pointer, all the way to 7 SP. SD6 goes from 8 SP all the way to 15 SP, and then and then X5 goes all the way from 16 offset of the stack pointer all the way to 23. And then after we do some procedure, in this case the procedure is adds, subtracts, maybe an add immediate. That's fine. What we do is we have to load that data again in order to restore the stack. So what happens is we have to load what was in the stack, or what was in the stack point, or we have to load what we calculated on. So we did these calculations, x20, x6, and x5. We load them into their respective positions on the stack pointer in the opposite way that we push them on, because they're going to be coming out in the opposite fashion. So x20 is going to come out last. Or sorry, x20 in here is on the top of the stack, so 0 SP now. So because we're popping everything off. And then finally we restore the stack pointer. So down here we did stack pointer minus 24. So when we restore all of this, we have to do stack pointer plus 24 at the very end to restore this. That way we don't wind up with any funny business going on. Okay. So then we can have nested procedures, which means we can have procedures that call procedures. So this gets a little confusing, but it's not unmanageable. If they don't call any other procedures, they are called leaf procedures. Let's see if they have a pretty picture for us to look at. Oh, doesn't look like it. Okay. So we can just go through some of this text. So for example, suppose that a main program calls procedure A with an argument of 3, and then procedure A, so let's write it down. So main program calls procedure A, and then A calls procedure B using another jump and link. So this leads to problems because, you know, these different procedures might use the same registers as each other, and so that's why there's this there could be conflicts over the return address in register X1. So we wind up with these situations that when we're doing these kind of nested procedures, when we're allocating more place on the stack, we also have to save the return address on the stack as well. That way, every different level of the nested procedure knows where it needs to return to first. So one solution to it, the naive solution, is to push all the other registers that must be preserved on the stack. So just shove everything on the stack. And do they talk about anything else in here? Nope. So that's the solution they give. So if you really need to preserve this data, if you really need to preserve this data, just put everything on the stack. You'll be fine. So stack is just, you know, that's our all-purpose tool for saving data while we're moving around procedures and jumping around programs. Okay. So okay, so let's tackle a recursive procedure that calculates a factorial. So what is a RISC-V assembly code? So they have a factorial, and let's see what they do. So the first thing they do is they allocate, so they adjust the stack to put two different double words on, x1 and x10, because when they call, they want this long int. They want enough space for this long int, which is a long 128 bits. Okay. So the first time factorial is called, it saves an address in the program they called fact. The next two instructions test whether n is less than 1. Okay. So then it tests, so it just does an add, and then it does a greater than or equal to test of -1. Okay, and then it does another add. So if n is less than 1, fact returns by putting 1. So and when you normally do a program that calculates a factorial, you stop when you reach 1 if you're doing it recursively. Then they pop those two items off the stack, and then they go back to the caller, which was whoever called factorial. Okay. And so this is a fairly intricate example. It would be more helpful if they had all the code in one contiguous block, but so because of that, we're not going to go through it anymore. So let's talk a little bit about the hardware-software interface. So a C variable is generally a location in storage, and its interpretation depends both on its type and its storage class. So there's two storage classes. There's automatic and there's static. So automatic variables are local to a procedure and are discarded when the procedure exits. So if you have a variable that's defined inside of a function, once you return from that function, it's discarded after the return. So static variables, they exist across, exist from entries to procedures in C. And so they use this keyword static. So that means if it exists in the function, it also exists in the caller of the function. It exists in both the caller and the callee. Okay, and so one of the registers in X3 is specifically the global pointer. So that's if we need to have some variable that's accessible in both. We have some global pointer that's shared among all of them. So it's a register that is reserved to point to the static area, so an area where all the static variables will live. And so here we have something that whenever you start doing any type of assembly programming, it's something that's very important to kind of look over. And it's whenever you're calling procedures, you need to know what is preserved and what is not. So there's saved registers. Those are going to be preserved. There's the stack pointer register. That has to be preserved because that's where we're storing our data that we're trying to transfer to a procedure. There's a frame pointer that's preserved. There's a return address that has to be preserved so we know where to go back to. And then the stack above the stack pointer is preserved. So anything that we loaded on the stack must be preserved. What is not preserved are temporary registers. You can think of those as local variables. And then the argument and result registers. So these are also not persistent. And then anything below the stack pointer is not preserved. So I don't know any situation where we would have something below the stack pointer or register below, or some values below. So allocating space for new data on the stack. The final complexity is that the stack is also used to store variables that are local to the procedure but do not fit in registers. So this is that idea of register spilling that we talked about earlier. The segment of the stack containing the procedure's save registers and local variables is called procedure frame or activation record. So let's look at figure 212. Okay. So we have the frame pointer and then a stack pointer. So before a procedure call, the stack pointer is directly below the frame pointer, or it's at the very bottom of this range. Then during the procedure call, we're going to do something like sub SP 24. So we want to move the stack pointer down and make some space. And then we load on local arrays, saved registers if any, saved return addresses, and then saved argument registers if any. And then after the procedure call, we of course have to increment. So we do the opposite of this. We now add, oh sorry, when I said sub here, it should have been, oh no, that was right. And then now we add. Okay, so that should be correct. Okay, and so a frame pointer, just like we have a specific spot a specific register that is associated with the SP, the stack pointer, we have one that associates with the frame pointer, which is x8. So that's convenient for us. Now let's talk about the heap a little bit, allocating space for new data on the heap. So in addition to automatic variables that are local to procedures, C programmers need a space for memory for static variables and for dynamic data structures. Okay, so dynamic data structures and static variables. So remember, these are, when we're talking about the stack here, we're talking about mainly local things. But when we're talking about the heap here, we're talking about these static things. Or static variables, variables that will exist continuously in both the procedure and the main program. So 213 shows the RISC-V convention for allocating memory or running the Linux operating system. So let's see what we have here. So we have the stack, of course, and then we have the dynamic data, static data, text, and we have some reserved space at the very bottom. So let's go through this a little bit. the stack starts at the high end of the user's address space. So we'll see that in chapter 5. And grows downward. So this is kind of like we already saw before when we had to decrement the stack pointer. So the stack pointer is already at some higher level, and we have to decrement it down. So it starts at the high end of the address space. So the first part of the low end of the memory is reserved, followed by the home of the RISC-V machine code called the text segment. So the RISC-V machine code, all the ones and zeros, that's going to be in something called the text segment. Above the code is the static data segment. And so this is a place for constants and other static variables. So we have this spot here. So this is reserved. This is going to, the text is going to be for instructions, and then we have static data, which is going to be our constants. So although arrays tend to be a fixed length and thus are a good match for static data, data structures like linked lists tend to grow and shrink during their lifetimes. The segment for such data structures is traditionally called the heap. Okay, and is placed next in memory. Note that this allocation allows the stack and heap to grow toward each other, thereby allowing the efficient use of memory as the two segments wax and wane. Okay. And so here we have this, we showed that the stack grows downward and the dynamic data grows upward. That's the stack and the heap. So C allocates in free space on the heap with explicit functions. So we're going to add some space for us on the heap with malloc, and we're going to get rid of it with free. Okay, and so a lot of time people will talk about memory leaks, and so all memory leaks mean is that we malloced something but we never freed it, and so we're going to continue growing and growing and growing and growing and growing until we hit a certain point where we could get some collision between the stack and the heap because they grow toward each other. Remember, they grow toward each other. Okay, so 214 summarizes the register conventions for the RISC-V assembly language. Okay, and they say that they're optimizing for the common case based upon this design. Okay, I guess we have to believe them. So, communicating with people. I think this is just about the last section. So, most people know about ASCII, and we have this very standardized way of representing very commonly used symbols by binary digits. And so ASCII stands for the American Standard Code for Information Interchange. So we could represent numbers as strings as ASCII. How does storage increase if the number 1 billion is represented in ASCII versus a 32-bit integer? So 1 billion takes 10 ASCII digits, which are 8 bits long. So every ASCII digit is 8 bits, or 1 byte, because we have 8-bit bytes. So the storage expansion, we're going to get 10 times 8 divided by 32, which is 2.5. So that's pretty big. We need 80 bytes just to represent this number, and 1 billion is not a very big number. My goodness. The other reason why we don't represent numbers, besides for doing something like input and output in ASCII, is because these ASCII numbers and their so the characters and their corresponding values, they mean nothing in regards to anything arithmetic related. But it's an interesting side note. Okay. So then they show some example of copying strings and how you would do that, which is fine. Characters and strings in Java. So Unicode is a universal encoding of the alphabets of most human languages. Given a list of Unicode alphabets, there is almost as many alphabets in Unicode as there are useful symbols in ASCII. To be more inclusive, Java uses Unicode for characters by default and uses 16 bits per character, so it uses twice as much space as ASCII. And so these are just some of the alphabets in Unicode. Okay. This is fine. A lot of this is not fairly interesting. We can kind of skip most of that. That's, mainly talking about ASCII and Unicode. As an architect, that's not really something that we'll see come up very often. That's more of just for some context of some things that computers do. So let's talk about wide immediate operands. In the context of addressing, for them. So RISC 5 instruction set includes the instruction load upper immediate to load a 20-bit constant into bits 12 through 31 of the register. So that means it only loads the upper bits of the 64-bit register. The leftmost 32 bits are filled with copies of the bit 31. So this is for sign numbers. So that means that if we have a number like 0, 1, 1, 1 get loaded in, that means that, let's see, in bits, so let's say if this is 12 and then ... and then we have, say, a 0 here, and this is bit 31, that means that the remaining bits will be 0. They'll just be a copy of this one. So if this was 1 instead, these would all be 1 out here. So this is just some sign extension. That makes sense. We can go over sometime why sign extension works. Okay, where's my highlighter? So what is a RISC-V assembly code to load this 64-bit constant into register 19? So we notice that this constant isn't particularly interesting. There's lots of zeros, and most of the data is at the very end. So we could load 12 through 31 with that bit pattern, which is 976. So what happens when we do that? So 976 is equal to this bit pattern we want up here for bits 12 through 31. Then we add the lower 12 bits, which are just going to be these, and then we're good. Okay, so let's talk about hardware software for a second. Either the compiler or the assembler must break large constants into pieces. I would guess it's usually the job of the compiler to do this. So it's either, but it says it's either the compiler or assembler. Hence, the symbolic representation of the RISC-V machine language is no longer limited by the hardware, but by whatever the creator of the assembler chooses to include. We stick close to the hardware to explain the architecture of the computer, noting when we use the enhanced language of the assembler that is not found in the processor. So addressing in branches. Is this useful? This isn't terribly useful. So we'll note a couple key features here, or a couple key things. So PC relative addressing. So let's find the beginning of this instance. Almost all loops and if statements are smaller than 2 to the 10 words. So the program counter is the ideal choice. This form is called program counter relative addressing, which means that we have some program counter, and if we want to go someplace, we go somewhere relative to the program counter. So if we want to go to some location of some procedure, we'll go to the program counter plus maybe 24, or the program counter plus 48. So that's what we mean by PC relative addressing. It just means we're addressing relative to the location of the program counter. And that's a very intuitive and very easy way to think about how we would get around. Okay, showing branch offset in machine language. This is, so we're really kind of going on the same thing. So let's look at the addressing modes. That's more interesting. So multiple forms of addressing are called addressing modes. So we have immediate addressing, where the operand is a constant within the instruction itself. So that means the address is just a constant that we give it. We have register addressing, which means that some register stores the address that we want to go to. We have base or displacement addressing, so this is similar to PC relative addressing, except instead of using the program counter, we're using some other register. And then for PC relative addressing, we're using the program counter plus some other constant to go someplace. Okay, so immediate addressing, like we said, we're just using some value that we give it. So for register addressing, we're just looking at the registers to know where we're going to point to. So that's going to store the data, or that's going to store our address. Base addressing, we're going to have some register, some arbitrary register, add to some immediate value to give us the location of what we want in memory. Then we have PC relative, where it's some immediate, and then the program counter, which is a special register, give us what we want in memory. So this is basically what addressing modes are. They're different ways to access different things. So when we're talking about register addressing, so this register, this code in here corresponds to this register. Immediate addressing, this immediate value here is the thing that we're going to use to do computing. And these last two are for accessing memory. I think I misspoke earlier, but yes, these last two are for accessing memory. The only difference between these two is that one of them uses the program counter, which is a special register, and one of them just uses an arbitrary register. So decoding machine language. So here, you know, there's plenty of tables out there, and this is all published. We can take just this binary string and we can find out that it corresponds to, say, add x16, x15, x5. We can say that we can kind of reverse engineer this just by looking at some tables. That's not that interesting. So here's something that we need. So we have the opcodes of the instructions, and there's a table someplace on the actual mappings of the registers to binary numbers as well. I think they're just in order though. So I think x0 is just 0, x1 is just 1, x31 is just 31 in binary. But yeah, so we'll kind of skip this because this is just going to be looking at tables and copying. I think this is one of the last two sections. So I think we're almost done with chapter 2. So parallelism and instruction synchronization. So parallel execution is easier when tasks are independent, but a lot of times they need to cooperate. And if we don't synchronize, which means if the two things don't talk to each other, even though they're doing things on maybe the same set of data, there could possibly a data race, which means that the results of the program could change depending on, who goes first in line. So a data race is specifically two memory accesses form a data race if they are from different threads to the same location. At least one is a write, and they occur one after another. So let's say we have two threads. So thread 0 and thread 1. Now with thread 0 and thread 1, what's going to happen is, let's say this guy sets some variable a equals 5. And this guy sets that same variable a equals 3. Okay, and this is the same variable. This is the same spot in memory, okay? So these are the same thing, these locations. Now, so at the end of the program, so the program completes. So what is a equal to? And the answer is, if there's a data race, we don't know. We don't know what a is equal to. Because a could be equal to 5, or a could be equal to 3. Because there's no synchronization. At least they did in a situation where they didn't write explicit synchronization. And so right now we bring in this concept of locks and unlocks, and we create regions where only a single processor can operate, called a mutual exclusion, or mutex. And then we also talk about some hardware primitives to do things atomically, which means only I have access to this location. This is it's my time to do something. Everyone else has to wait until I give up a lock, and then you can come in and do something. So there are a number of alternative formulations of the basic hardware primitives, all of which provide the ability to atomically read and modify a location, together with some way to tell if the read and write were performed atomically. So that's important. Let's start with one such. So let's look at atomic exchange, or atomic swap as it's called. This is a very common thing. Do they talk about it down here? Okay, they don't show it that well. Okay, so we want to build a simple lock, and we're going to utilize atomic exchange or atomic swap. So a processor tries to set the lock by doing exchange of 1. So in this case, we have P1, and it wants to exchange, so it has a 1, and let's say P2 has a 1, and then let's say some piece of memory or something has a 0. So what happens is P1 tries to do a swap with M, so we'll write that as P1 swap M, and what happens is, if M is 0, meaning nobody's locked it out, P1 will get the lock and now be equal to 0, while M will now be equal to 1. So let's say further down the line, P2 comes along. So P2 does the swap with M, but P2 is still equal to 1 now, and M is still equal to 1 now. So what this tells P2 is that I didn't get the lock because I'm not 0 yet, and M1 is, M1's fine. M1 has the same value it had originally, so it doesn't change regardless. But yeah, so this is the basic idea of how locks work and how atomic exchanges work. So if two things come in at the same time, so if P2 does an atomic swap, or so if P1 does an atomic exchange with M even if P2 comes in before this completes, P1 is going to finish. It's guaranteed. Okay. Okay. And a lot of that is just some explanation of how that works and why we need that. So although it is presented for multiprocessor synchronization, atomic exchange is also useful for the operating system in dealing with multiple processes in a single processor. To make sure nothing interferes in a single processor, the stored conditional also fails if the processor does a context switch between two instructions. So this basically says that when we do a context switch, we're supposed to swap out, all the information from, say, one context for another's context. But if we've executed an instruction that relies on that previous context, we're going to have some problems. So an advantage of the load-reserved store conditional mechanism is that it can be used to build up other synchronization primitives, like compare and swap, fetch and increment. These are just many different ways of doing a similar thing. So atomics are a very useful thing, and it would be interesting if I could do a little series on atomics and a little series on synchronization. I think that could be useful. Okay, so moving on. So translating and starting a program. So this will be the last section that we're going to go over for this chapter, because a lot of the rest are just kind of examples. So let's look at, taking a C program and going into and turning it into assembly. So of course we have to start at the C program, where we go to a compiler. At the compiler, we do some optimizations to make some efficient assembly. The assembler itself, which really knows the instruction set, that's going to create two things. It's going to create an object of the machine language module and then an object of the library routine in the actual machine language. The linker is going to put these together, take these two things, create an executable that's in machine language. Then the loader is going to take this executable and put it inside memory. And then once it's inside memory, that's how it can be executed. Okay. So a little bit on the compiler. And so the compiler just transforms a C program into assembly language. That's about all we really need to know about that. The assembler. Since the assembly language is an interface to higher level software, the assembler can treat common variations of machine language instructions as if they were instructions in their own right. So it can create pseudo instructions to simplify the assembly language. Okay. So when it makes these things, and for branches, so assemblers keep track of labels used in branches and data transfer instructions in a symbol table. So you may have seen this sometime if you're doing something, if you fail to link if you fail to link a dynamic library and it can't find the path to that dynamic library, and you call the function, a lot of times you'll get the error you'll get is that the symbol table lookup failed, and that's because it can't find informations to execute that function. And so, like I said, so it's a table of symbols and instructions. So the symbol table itself, this is going over, and this is over object files. Then we have the linker, and so the linker, also called the link editor, a systems program that combines independently assembled machine language programs and resolves all undefined labels into an executable. So this is what kind of patches everything together and puts it into that executable you want. So when people say that, a lot of times people say like GCC is a compiler. So GCC isn't a compiler. GCC is a lot of things. It's your compiler. It's your linker. It's an entire package. So then we have, okay, so this is just an example. Then we have the loader, and the loader is what puts things in main memory. And so this is what I was talking about earlier, dynamically linked library. So they're called DLLs. In Windows, a DLL will have the extension .dll. In Unix systems, it'll be .so, I think. I think that's correct. Okay. And then they have another example for Java. And for the Java one, we'll basically stop here and just kind of go over this. So we have a Java program that goes to a compiler that makes Java bytecode. And then you have, separately, you have the Java library routines. So what happens is the compiler takes what you wrote and all the class files and puts it into Java bytecode. Java bytecode gets sent to the just-in-time compiler. So when the compiled Java methods are executing, it's getting information from the Java just-in-time compiler, and all of this executes within the Java virtual machine. Now, if someone knows Java more than me, they might have been able to explain that better. So we can just kind of go through the caption of it. So it's first compiled into binary version of Java bytecode. Then the Java program can be run on the interpreter called the JVM. So after it's in bytecode, it can be run on the virtual machine. So the just-in-time compiler is for additional performance benefit. And so what I mean by additional performance benefit is that the Java virtual machine can invoke the just-in-time compiler to compile certain methods. So there's some communication right here. So it says, the Java virtual machine says, okay, just-in-time compiler, I need you to make this faster for me. And so it can compile these methods into the native machine language and then give it back to the Java virtual machine. Okay, great. So it looks like we've gone through all of chapter 2. The rest are mainly examples and some arrays versus pointers. These are mainly just the applications of all the topics that we learned across this chapter. This is chapter 2 of Computer Organization and Design. I think it's what is it? A hardware-software approach using RISC-V instruction set. So let's see what we're going to be doing next time with Engineering Today. Okay. So lots of examples. They do lots of examples in this book, which is really, really good. Okay. My goodness, where is the new chapter going to begin? Here we go. Okay, so next time we're going to be going over arithmetic for computers. So here we're going to start getting into the real architecture. Most of the stuff we've learned recently has been the more software side of architecture. It's been, okay, let's learn about instructions. Let's learn how a C or Java program gets turned into a machine ISA, or how it executes on real hardware. But we haven't talked about designing the hardware itself. So the processor that we're running on, how do we run how do we create that? The arithmetic units that do the operations, how do we make that? So that's the kind of stuff that we're going to be doing next time on the stream. So we'll be back tomorrow around the same time. I would think around 4 to 5 p.m. tomorrow, and then we'll probably go for another 3 or so hours. This went about 4 hours. It's a little longer than I was expecting. So yeah, listen, if you like the content, there's a YouTube link below that'll take you to the Engineering Today YouTube channel. I post all the VODs from Twitch onto that channel. I have additional content dealing with research on that channel. There's not a ton of content there yet, mainly because this channel is only a few days old. It's about 3 days old, 3 to 4 days old, as far as having uploaded content on the channel. So yeah, you know, give the Twitch channel a follow as well, that you're here. If you like the content, if you ever want a specific topic covered. So personally, I'm a PhD student in computer engineering. My research area deals with GPU microarchitecture. So a lot of the work that I do deals with making fault-tolerant GPU architectures, as well as secure GPU architectures. And we try to make sure that when we make a secure GPU architecture, we don't invoke too much of a hit on performance. Now, just as a reminder, we also will be doing numerous other books on this channel. So right now we're doing Computer Organization and Design with RISC 5. This book right here, the RISC 5 edition. So we're going to be going through this entire book. We just finished chapter 2. So chapter 2 is going to be uploaded. I'm going to export as soon as I cut off the stream, and it's going to be on YouTube. So other than computer organization and design, we're going to be going over operating system concepts. This is a classic operating systems textbook. We're also going to be going over crafting a compiler, a very classic introductory book on how do we actually make the compiler that we were talking about today. We're also going to be going over computer networks, which is a book on computer communication networks and how those are designed and created. So that'll be fairly interesting. That'll be a new topic for me as well. Okay. Then we will also have content for introductory computer engineering, which will be on fundamentals of logic design, a book that a lot of universities use. It's one of the first. It's one of the first computer engineering courses that I took when I was in my undergrad degree. And then finally, we're going to be going through this book, Digital Integrated Circuits: A Design Perspective, by Jan M. Rebe. And so this book is going to be a introductory book on integrated circuit design. And so we see we're going to go through, you know, how would we manufacture these integrated circuits, some design considerations when we're when we do this fabrication, and how do we make certain components. So this one will be interesting. This will also be a new experience for me. But as far as everything else, that's going to be the stream for today. Thank you all for joining me. And as always, I hope you learned something new. Ciao.